Post lunch session, we will be having 5 streams of oral presentations today. We have organic and biomolecular chemistry stream, which will be chaired by Professor Jai Kumar Kandaswamy from IIT BHU. And then we have nanomaterial stream, which will be chaired by our own Professor Padmanabhan. And then we have computational chemistry stream running, which will be chaired by Professor Swati from IISER Trivandrum. So we'll start the day with the prayer. So I request Devjit Jyoti to sing a prayer song.
Vakratundam Mahakayam Suryakodi Samaprabham Nirvignam Gurume Deva Sarvakareshu Sarvada Dhyayamo Dhavalabagundhanavati Tejomayi Naishtiki Snigdha Pangavilokini Bhagavati Mandasmita Srimukhi Valsalyamritavarshini Sumadhuram Sankirtanalabhini Shamangi Madhusnigdha Suktim Amritanandatmikameshwari 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 Om Amriteshwari Namaha Om Amriteshwari Namaha Om Amriteshwari Namaha.
Thank you, Devjit, for this blissful prayer. So let's start our day with the first plenary talk. We have Professor Boris Karisov today with us. I request Dr. Beena to give a brief introduction about Professor Boris.
Naveen sir, am I audible?
Yes, ma'am, you can. Go ahead.
Okay. Very good morning to one and all. It is my pleasure to introduce Dr. Boris Karisov, professor and researcher at the Autonomous University of the Nuevo Leon, Mexico. Dr. Boris obtained his PhD in inorganic chemistry from Moscow State University, Russia in 1993. His research interests include nanotechnology, electrosynthesis, and ultrasonics. He has to his credit about 185 papers, 10 patents, 13 books, and 14 book chapters. Dr. Boris is also a member of the editorial board in several reputed journals. He is associated as a member of Mexican Academy of Science, National Researchers System, and Materials Resource Society. Dr. Boris has been a part of the recovery works happened due to the Chernobyl accident in 1996. His biography was published in Who is Who in the World and Outstanding People of the 20th Century. It is great pleasure to have Dr. Boris with us. Today he will cover the topic metal organic framework derived nanocarbons, synthesis, properties, and application. Now over to Dr. Boris.
Thank you so much. Can I start? Yes?
Yes,
Okay.
Boris.
Good morning, dear professors, researchers, students, ladies and gentlemen. Let me talk to you today about MOF-derived nanocarbon properties and applications. More complete description of this presentation you may read in this book, which is in the lower part of this page. We published this as a book chapter last year. Just a moment. If some students are hearing me now, I would like to tell them about the definition of MOFs, the class of crystalline materials that consist of coordination bonds between transition metal cations and organic linkers. And MOF structure is open framework. It can be highly porous, and porous materials are frequently derived from the MOFs. This information for students, and in advance I would like to invite students to join us in Mexico, and about this I will tell you at the end of this talk. About MOFs, as you might know, there are about 70,000 MOFs discovered for the last 30 years, in particular, more than 20,000 reports describing these and many other MOFs, which you can see here in this picture. They are multidimensional structures with a large surface area and high porosity. And the MOFs are, of course, very useful. They have many applications themselves, but also after pyrolysis, MOFs can be transformed to metal and metal-free and metal carbons, carbon-based materials. And, of course, metal species can be deleted, can be removed via acid leaching, and here we can obtain all carbon-based, highly porous and conductive nanocarbons, practically starting from every MOF. Being combined with typical radiometallic compounds, coordination radiometallic compounds, MOFs, their derivatives are much more stable in comparison with these precursors, and they can contain metals, metal oxides, even some rests of salts, metal salts, in case if the anion it's impossible to remove from the carbon, from the carbon. And it is possible to manage the carbon pore structure, adding before the pyrolysis additional carbon sources like this one, fluoride alcohol, glucose, organic carbon-rich compounds. Being added to the MOFs prior to recarbonization, it's possible to obtain MOF-derived nanocarbons with high nitrogen content and high porosity. About general methods for the preparation of MOF-derived nanocarbons. Most classic MOFs, MOF5 and ZIF8, these compounds, these MOFs are most frequent. They are used in order to obtain the derivatives, nanocarbons in different forms. And the pyrolysis is generally carried out about 1000 Celsius, and adding some organic compounds in the pores of the initial MOF precursor, it's possible to obtain highly porous carbons from these two MOFs, and of course, from many other MOFs. As you might know, nanocarbons can contain various types of defects. For example, the presence of nitrogen is obviously such defect, but indeed the presence of many atoms of nitrogen is not bad. It's indeed very good because can lead to the many applications, useful applications, in particular as cathode material for zinc-iron batteries or lithium-sulfur batteries, among many other applications. Here, the templates can be coated with MOFs, in this case, LIF8, and this organometallic compound can be synthesized in situ on the surface of templates with silica. Silica here can be nanoparticles of silica or microparticles of silica, and then silica is stable under thermal treatment, and organometallic compound decomposes, forming carbon on the silica templates. The surface area of formed nanocarbons can vary a lot, and even 1,000 square meters per gram is much surface area. But in case of more and more, it's possible to reach almost 4,000 square meters per gram. And these products can have high electrocatalytic activity, thermal resistance. They can serve as to store hydrogen, to store carbon dioxide, absorb its molecules, and to be used as the catalysts, in particular for the interaction of acetylene and hydrogen chloride. And Z8 can be a precursor to use compounds with zinc nanoparticles or zinc oxide nanoparticles. It depends on the conditions of the synthesis. In case of use of steam atmosphere, it's possible to obtain zinc oxide nanoparticles embedded in doped nanocarbons. Okay, and in this case, it's possible to obtain homogeneous nanoparticles of zinc oxide in the carbon matrix, and this material has a strong affinity for the molecules of carbon dioxide. And in addition, this material could be used for the degradation absorption of several contaminants like methylene blue dispersed in water. This is very important for the textile industry, and I observe in the literature many papers from Indian authors about the use of MOF-derived nanocarbons precisely for the destruction of several paints which are in wastewaters from textile industry. And range of temperatures for the preparation of MOF-derived nanocarbons is vary from 400 to 2,000 degrees, but the most common range is from 700 to 1,000. The best temperature in which we are working is from 800 to 900 Celsius. In this case, we can observe maximum concentration of n-doped atoms and other useful defects in the nanocarbon structure. What are the structures of nanocarbons? According to SIMA team studies, quite different geometrical figures can be formed. Here you can see in form of the cuboids, but other polyhedrons also can be foams, bamboo-like carbon tubes, nanofibers, spherical particles, sheets, and not many others, including, of course, carbon nanotubes, fibers, and practically all dimensionalities can be formed from 0 to up to 3D. ZIF-8 carbon nanosheets is a typical example of 2D dimensionalities. The nanosheets, this is now not a rare nanostructure, but here sometimes it's difficult to obtain 2D two-dimensional structures, but here it's typical example that it's possible from MOFs, ZIF-8. And in this case, they have a high electroconductivity and can be applied as in lithium batteries and other. Other varieties can be whole structures of composition composed with several metals, metal oxides, metal salts, even with noble metal nanoparticles. So metal nanoparticles can be successfully used in the process of drug delivery, in particular, for medicine purposes. Okay. Varying the calcination temperature, we can manage the properties of MOF-derived compounds. Obviously, this is not the only factor influencing in the properties of the final products. Okay. Other factors are the structure of MOF, presence of impurities, even synthesis temperature of the same MOF before its pyrolysis. And obviously the pyrolysis temperature, calcination temperature also. This principal factor, but not the only factor. If we heat more than 1000 Celsius, we can get the porous structure. At lesser temperatures, the porosity is generally less, but it can vary for different MOFs. Even graphene quantum dots, doped with nitrogen, can be formed. They are soluble in water and applied in photocatalysis and sensors, biomargin, other medical and non-medical applications. Here it's they can have impurities, not only nitrogen but oxygen and other atoms. So the presence of nitrogen, this is one of principal factors, but not the only factor which influences in the properties of the final products. A special case is the MOFs containing magnetic metals, such as cobalt, iron, nickel, or their combinations, including ferrites, which can be formed in situ during calcination or before, or they can be added after thermal processes. Indeed, when the magnetic metal and hydrogen and oxygen atoms are present in the initial MOF structure, several types of defects can be formed. Several groups, species like these ones, zero-valent cobalt, divalent cobalt, cobalt is connected OH groups, and other. Magnetic properties are very useful even for the catalysis, in particular for the catalysis purposes, because it is relatively simple to remove the catalyst after the completion of reaction. But don't believe to this. Indeed, if the nanoparticles are well suspended in solvent and solution, they sometimes do not want to go to the magnet. It's sometimes difficult to manage them through magnetic forces. In one application, we work several years, last years, in the oil remediation water and magnetic remediation of nanocarbons with oil particles absorbed by carbons. Is one of the useful methods for remediation. For separation oil and water, also degradation of dyes in water, catalysis, integration of hydrogen, among many other applications. Such reactions like oxygen reduction reactions, hydrogen evolution, and similar, which correspond to water splitting. We will talk about this later. This is an example of these reactions and the structure of the final products. Here we see tubes in the form of rectangles and the particles of this carbon, which contains cobalt. So these products can be, in case of being hollow structures for the absorption of gaseous, liquid, and liquid impurities, they are very useful. Now we don't talk about the cost, the prices of MOF-derived nanocarbons. Obviously, they are not low. We are talking about possibility to improve their absorbent characteristics. For example, here, this MOF can be synthesized at relatively low temperatures, but the calcination temperature should be also always high, at least more than 500 degrees. But several organometallics, for example, please see the reaction below, can take place in low temperatures. Well, of course, this compound is not MOF, this typical organometallic compound, but the result could be similar. The formation of graphite-like species, magnetic, because iron oxide is present and is mixed with graphite. And the properties of this composite, this material, is also as absorbent and for elimination of several contaminants from water. Iron and iron oxides, being in the nanoparticle form, can act as destroyers for a variety of organic and even inorganic compounds. So and iron compounds are non-toxic, being compared with other nanoparticles. It's a serious advantage. So the iron is widely used as a nanomaterial, zero-valent iron and its oxide. In this slide, you can see the pyrolysis of oxygen-containing MOFs at high temperatures. In this case, the graphite oxide phase can be formed, and also it has great absorption capacity for several dyes and pharmaceuticals. Elimination of pharmaceuticals is also great challenge, because some wastewaters can be contaminated with these molecules too, paints and pharmaceuticals. Okay, so here it's very important the presence or absence of several atoms, like here it's oxygen, nitrogen, phosphorus, sometimes but most frequent datum is nitrogen, which influences in many applications and contributes to the applications, for example, in batteries. Okay. About bimetallic derived carbons. This area is a niche for the further research because not many compounds with 2 or 3 metals have been reported up to date. We started this work and we have several publications precisely with copper and nickel, but this is not our work. This is the work publication report from the literature. Several ligands are capable to form bimetallic compounds. Here, indeed, is not so important. Is the final compound before pyrolysis? Is the individual compound bimetallic compound, or this is mixture of individual MOFs with, for example, copper and nickel? One and another can have similar structures, and especially if the metals have the similar ionic radius and oxidation number. Preferably to have individual compounds, of course, but here, as I said, this for the structure of the next product, nanocarbon, this is not an obligatory factor. Okay, and, the nanocarbons which contain 2 or more metals possess extremely high catalytic activity. 2 metals always work better in comparison with individual metal atoms. Obviously, they have large surface area, high stability in alkaline media, and frequently it is compared with platinum-based materials. And nanocarbons which contain non-precious metals, they are compared with expensive platinum-based materials. Frequently, the properties of these nanocarbons containing, for example, copper or nickel are better and cheaper being compared with platinum-based materials. Another example in zinc and cobalt. This compound is magnetic, and you can see here, you can say nanorods. Nanorods are able to prevent expansion of the materials. They are like building blocks, like iron structures in the construction of house. Yes, similar function they have here. We know that, for example, the batteries for cellular phones sometimes expand, and it's impossible to continue using. In the modern batteries for cellular phones, this problem is had been resolved with no expansion. In particular, some structures like this one prevent the expansion of the material during the processes loading, unloading current. Here, at atoms like nitrogen have the principal role in such properties. Since MET is a template-based solution route can be used for lithium-ion batteries. Indeed, there are a lot of methods, since methods technique is for the derived MOFs and MOF-derived carbons, but the pyrolysis is the principal method. The pyrolysis can be carried out not only by spray pyrolysis, but it can be carried out using microwave irradiation. There are several mob-derived nanocarbons obtained by this way. I talked about end-doping. That is very important, extremely important, and such properties as selective conductivity, increase the charge transfers, and many other properties can be depend on the presence and quantity of end-doped atoms. And these materials can be manufactured in a mixture of gases, for example, argon, nitrogen with ammonia, and in a range of carbonization temperatures. Several bimetallic compounds can be obtained by this way. In this case, is cobalt nickel MOF, also magnetic. And in the MOF-derived nanocarbons, one atom can be zero valent, another atom can be in the form of divalent, for example, or both can be zero valent. It depends on the conditions. As we see on the right side below, the N atoms can be formally have different nature: pyridinic atom, pyrrolic, graphitic. They can have different properties. So, changing the conditions of pyrolysis, condition of synthesis, we can increase the part of some, for example, the graphitic atoms, decreasing the part of pyrrolic atoms, and change the properties on the final products. So, in addition to these N atoms, you could have a lot of varieties of oxygen atoms in the form of ether atoms and cetone atoms and peroxide and so on. So defects here are can be a variety of defects in these structures. And for example, graphene, carbon nanotubes, all nanocarbons practically can have defects, and many atoms forming different type of defects and different properties. That's why the nanocarbons are so interesting, and here we have a lot of opportunities. One example about end-doping. Before pyrolysis, after pyrolysis, and typical some image of 7-10 images of the MOF-derived nanocarbons. Main applications of MOF-derived nanocarbons are here. We work in the water separation, oil-water separation. We have just started CO2 capture and its conversion to carbon monoxide using bimetallic MOF-derived nanocarbons. But there are a lot of other applications. And of course, the surface area is quite different. Here we have, for example, not our work, about 2,000 square meters per gram. This can be used at carbon electrode. And, metallic nanocarbons are rare, but you can find reports about them also. They're useful in the oxygen evolution reaction processes. Graphically, some applications of MOF-derived nanocarbons are here, and I will talk now about some catalytic applications of them. For me, it's very interesting photocatalytic applications and in particular water splitting. General information about catalysis using carbons. This is synergetic effects of carbon, nitrogen, and metal atoms can be observed. They described, widely described in reports. High porosity solvents and unique structures, and, good, excellent catalytic performances are typical. Highly dispersed heteroatoms can influence, and it's possible to vary the addition of carbon and N atoms, additional carbon sources, and high porosity is the main property of the nanocarbons, in particular derived from MOFs. Here you can say this may be metal or metal oxide decorated commas, or metal and metal oxide decorated commas. So the presence of metal and oxide at the same time leads to several useful properties which are used in the electrocatalysis or heterogeneous catalysis also. As an example of heterogeneous catalysis, conversions between carbon oxide and dioxide. Sometimes it's necessary to obtain monoxide from dioxide and vice versa. And several catalysts, composites, bimetallic composites, derived from MOFs, they have high catalytic activity, and so oxidation or transformation of carbon dioxide into carbon monoxide. Here such a reaction as saline hydrochlorination can be also carried out using catalysts derived from ZIF8 by carbonization. It contains bamboo-like carbon nanotubes from 40 to 80 nanometers in diameter, highly dispersed particles, and can be used as an effective catalyst for these reactions. And such reactions have been described in the reports, many reports. This MOF transformed to the mesoporous carbon with size of particles about 50 nanometers is useful for these two important reactions, chlorophenol and nitrophenol. Electrocatalysis. There are a lot of examples, and meanwhile you are reading this slide, I would like to mention that acidic conditions seriously affect stability. Meanwhile, operations of fuel cells require low pH, but more direct nanocarbons are low stable because the metals which are as dopants, they are dissolved in the acidic medium, so they cannot work at these temperatures, these pHs. Sorry. So this is a niche for the further investigation of the catalysis area. Ideally, it's necessary to have catalysts for all pH range, but we know this is so difficult. For example, even at 4 or 5 pH, the metal can be dissolved. How to reach the stable metal at pH 3 or 2? It's high acidicity. In the at pH, for example, 9 or 10, no problems, but here low pH is difficult. But indeed, MOF-derived nanocomets are much more stable in comparison with their MOF precursors, so thermally stable and chemically stable. What is the MOF? MOF is a metallic compound which is can be sensible to water, to oxygen, sometimes to the everything, solvents. But nanocomets are generally much more stable, but not at all pHs. Some examples. Div-67, they can be used in these type of reactions, water splitting. And, about nanoflowers, second paragraph. Nanoflowers are intensively used during the last 10 years, especially in the last 5 years, because they have surface area extremely high in comparison with other nanostructures. So, now there is not so difficult to synthesize them. And, water split is one of the main areas, very important, because obtaining of oxygen and hydrogen is, from water is one of the principal goals of the humanity in order to have free energy, hydrogen. For many years, this area is being developed. About environmental remediation, I already mentioned it. Degradation of pollutants, reduction of carbon dioxide, water splitting, other organic transformations. So this also niche from intensive further mitigations. Last paragraph here. At this moment, there are several reports in this area, but indeed this area is not so developed, very good. So in each area it's possible to see something bad developed, which requires further efforts. So this is one of them. Some observation about catalysis driven by nanocomets. I already talked about easy, so-called easy removal from the reaction mixtures. Don't believe to this when you see in articles it's always easy and simple. Indeed, I worked with ferrites, with iron nanoparticles, and iron oxide. Sometimes these magnetic metals and their compounds do not respect magnetic forces. They being well suspended in the solvents, in the solutions, is difficult to remove them fast. It's necessary to wait some days before the particles of these metals goes completely to the magnet. So it's not so easy. Okay. But comparing conventional porous carbons with MOF-derived carbons, practically all is in favor of the MOF-derived nanocarbons. Nitrogen content is superior, is absorption capacities, surface area, catalytic properties, absorption properties, and so on. Reading literature about catalysis using MOF-derived nanocarbons, a special challenge is single atom carbon catalysis, SACS. This is also a serious niche for further investigations. And there are not many reports in this area, and I highly recommend to those students, for example, PhD students who don't know about their further theme of dissertation of PhD, to dedicate to this theme. It's very interesting, extremely interesting, and not well developed up to date. So it's a serious niche for further investigation in this area. Also, I would like to talk about DFT methods and their applications for calculations of MOF structures, determination of their architecture.
there are a lot of reports for the MOFs. Meanwhile, for MOF-derived nanocarbons, a lack of profound investigations, theoretical investigations, is currently observed. They belong mainly to the electrocatalysis area, and sequestration of carbon dioxide and sources of organic substance, and nothing more. Other studies are very rare. However, before spending some weeks or months for the experimental part, it's possible having this experience to calculate or make simulations using special programs. We live in the century 21, and now the computer base of for such predictions is strong. I myself I'm not dedicated to this one, but we have some persons who help us to make such calculations and simulations. And indeed, there are many opportunities before starting experimental work. Obviously, not any theoretical calculation can be realized, can be carried out practically. Okay, but indeed, it's possible to make several predictions for the MOF-derived nanocarbons. Sorry. Expecting the return to the slide. Okay, sorry. As one example, I would like to mention this composite which contains cobalt, phosphorus, and carbon-induced composite. Using the Vienna ab initio simulation package, with a standard package which is used by the majority of specialists in this area, it was predicted that this electronic structure of this nanocarbon can be modified by a gradual dopation by nitrogen and phosphorus. This is a typical example of dopation with phosphorus. Other elements, in addition to nitrogen and oxygen, are rare as dopants. So this is one of examples of phosphorus doped nanocarbons. So it's possible to predict their further uses, in particular in devices, and properties of the forward nanocarbons on the basis of this composite cobalt and phosphorus. Our recent publications in this area, they are here in the catalysis, the review articles, some experimental articles, and book chapters. This is the first experimental articles which was published in the area of nanocarbons with copper and nickel, and reviews and chapters. And last year we published this book about carbon allotropes, which this book contains information about classic carbon nanostructures, about less common carbon nanostructures, about DFT, predicted carbon nanoforms, coordination with organometallic chemistry of nanocarbons with metal complexes, stabilization of carbon allotropes. In this case, we have a book published in Springer in the year 2018. Carbon allotropes in the environment, their toxicity, applications, and a big chapter for students. If the students are here in Minau, so they can find a lot of experimental material here in the chapter number 11. And
to see some practice, and professors can find here in this chapter can find several problems and which they could offer for students in the classes. Okay, so this is a book about carbon nanotropes and their organometallic chemistry. Here we try to unite, to comprehend all available information about various types of, for example, rare nanostructures, nanobuds, nanopencils, nanocones, bottles, belts, flowers, mushrooms, forests, palms, webs, spindles, nanotechnical structures, fuses, for example, and balances, and so on. There are about 200 different forms. Is talking about predicted carbon forms. About 500 carbon nanostructures have been predicted up to date, and some of them were then discovered experimentally. But the major part of these compounds it is only theoretically. About our university, we are located in the north of Mexico, in the state of Nuevo León, New Lion in Spanish. Language is Spanish, and our university, obviously, it is closed now because of pandemic. All the classes we have online by Teams. Like now, we have about this amount of students. We are already at 200 kilometers from the border with the United States, with Texas. Very hot climatic conditions, from 5 up to 43, 45 degrees in July or August. This place in Mexico is not the hottest place. Here, much on the left, to the Pacific Ocean, the temperatures can be 50, 55, but here in Nuevo León we have about 45 maximum temperature. Currently, we need international students for postgraduate division. This is a requisite for us because the CONACYT on the right upper, CONACYT is National Council for Science and Technology. This organization financiers all scientific work in Mexico. So they requisite that we need to have more international students which who will do PhD and master science thesis. So if some students are hearing me, I invite them to study Spanish first and then to apply to the CONACYT in order to have a scholarship at our university. In addition, I offer all professors and researchers to prepare your book proposals for the CRC Press, where I take part as the series editor in the area of engineering. So you send me your proposals in these areas or any other areas, much more areas which are emerging areas in the century 21. So it's my personal invitation to you, and thank you so much for your attention. And if you have some questions, I'm ready to. I will try to understand. If somebody speaks Spanish, you may ask me in Spanish.
Thank you very much, Professor Boris, for your time and taking us through all the research you and Professor Oksana's group is doing from a while. So I think we are actually out of running out of time. So what we'll do is, if you have questions, I request the participants to write email to Professor Boris. His prompt, he will reply you soon. So I think because I see Dr. Ajay Ghosh is already in the, yeah, I see him on the forum. So we'll go to the next speaker. Thank you. Thank you, Boris. Thank you very much.
Thank you. Goodbye.
So our next speaker is Dr. Ajay Ghosh from CSIR NIST, Trivandrum. I request Dr. Akhil Shivan to introduce Dr. Ajay Ghosh to the audience.
Thank you, sir. Sir, am I audible?
Yes, sir. And go ahead.
Okay. It's with great pleasure and privilege that I welcome Dr. A. Ajay Ghosh to the International Conference on Advances in Material Science and Chemistry, organized by the Department of Chemistry, School of Arts and Sciences, Amrita Vishwavidyapeetham, Amrita campus. Dr. A. Ajay Ghosh is the director, CSIR NIST, Trivandrum, Kerala. He obtained his master's degree in chemistry in 1984 and PhD in 1989 under the supervision of Professor V.N.R. Pillai from the University of Calicut in solid phase peptide synthesis. He joined CSIR NIST, formerly RRL, as a scientist at the Photochemistry Research Unit in 1988 and later became its director in 2015. He is also a visiting faculty to many universities and research institutes in India and abroad. His major research contributions are in the interdisciplinary areas of organic photoresponsive materials, supramolecular chemistry, molecular self-assembly, organogels, and molecular probes and sensors. He has produced more than 30 PhDs so far and has got more than 170 peer-reviewed international research publications with a total of 13,000 plus citations, more than 10 patents, and having an H-index of 60. He has also secured more than 5 crores of research funding from various national and international agencies. Dr. A. Ajay Ghosh has published large number of research papers in the journal Icamsc Chemie, for which his author profile has been featured in the same journal. His research contributions are recognized with several prestigious fellowships and awards. The most notable are INSA JSPS Exchange Fellowship in 1993 and 2003, the Alexander Humboldt Fellowship in 1994, DST DAD Exchange Fellowship in 2001, Shanti Swarup Bhatnagar Prize for Chemical Sciences in 2007, MRSA Medal in 2007, the Infosys Science Prize, also known as the Indian Nobel Prize, in 2012, where he is the first ever chemist to receive that, the CSRI Medal in 2013, the TWAS Prize for Chemistry in 2013, the J.C. Bose National Fellowship in 2015, and the Indian Society of Chemists and Biologists Award in 2017. He is a fellow of the all three major science academies of India, an honorary fellow of the Kerala Academy of Sciences and fellow of the Royal Society of Chemistry, London, and the World Academy of Science. Since 2013, he serves as an associate editor of Physical Chemistry, Chemical Physics, an RSC journal, and a senior editor of the Bulletin of Chemical Society of Japan. He had been in the editorial board of Chemistry, an Asian journal, ACS Applied Japan, Material Interfaces, and Journal of Chemical Sciences, and the advisory board of RFC Advances. He is a life member of CRSI, MRSI, and SPS India. He is also a vice president, Society for the Polymer Science of India, and the president for its Trivandrum chapter. Apart from all the research activities, he is actively involved in the science education, science popularization, science awareness programs, organizing conferences, workshops, etc. With all these words, and on behalf of the Amrita Vishwavidyapeetham, Department of Chemistry, ICAMSC 2020, and myself, it's a pleasure to welcome Dr. A. Ajay Ghosh to deliver his keynote talk in the topic, Stimuli Responsive Supramolecular Functional Materials. Over to you, sir.
Thank you and good morning. Am I audible to all of you?
Yes, sir.
Okay. So, thank you for the kind words of introduction. And also I take this opportunity in thanking Professor Naveen Kulkarni and also Professor Padmanabhan, who is a friend and well-wisher of me, for inviting me to this conference and requesting me to give a lecture. I'm now going to share the slides. Let me know whether it is visible.
Yes, sir. Yes, sir.
Yeah.
It's all set.
It's all okay. So, this is a very, very difficult and, a crisis for all of us across the globe. So we are confined to the four walls where you are and using all the modern techniques to correspond. And honestly speaking, I would like to go to the conference site and then directly talk to the audience so that, I feel some vibrancy. But for me, this is like a very, very passive exercise, but we don't have any other option. So we are learning new things. And so sitting from this, distance, I will try to make an attempt to convey certain things about the chemistry that we are practicing at the National Institute for Interdisciplinary Science and Technology. Also, I understand this conference is a broad, chemistry materials conference. Materials science is like an ocean. Everything is materials and everything is chemistry. So both are synonymous. So where there is a material, there is a chemistry, or where there is a chemistry, there are so many materials. So yesterday, probably you must have heard a large number of lectures on different topics related to materials. Today also you heard another talk before me. I practice, soft matter chemistry. So we do a lot of research in the field of supramolecular chemistry and functional materials. So today I decided to talk a little bit about stimuli responsive, for supramolecular functional materials. So before I do so, I would like to briefly tell about the institute that I am coming. So this is a National Institute for Interdisciplinary Science and Technology, which is one of the constituent laboratories under the Council of Scientific and Industrial Research. Probably many of you may be aware of this institute, and at least a few of you must have previously visited this institute. So if you get any chance, maybe at a later time, please do visit the institute and learn more about the institute. So this is an interdisciplinary institute. So we have many interdisciplinary activities in the institute. We have 5 major research divisions in the institute, chemistry being the central, subject, which is very strongly connected to materials, environmental technology, agro-processing technology, and microbial process and technology. In the field of chemistry or in the chemical science and technology divisions, we work on different types of materials, mainly organic materials, such as photonic materials, organic electronic materials, fluorescent materials, molecular probes. We do a lot of chemical synthesis, drug intermediates, APIs, etc. We work on natural products and phytochemicals. So the chemistry division has a lot of different kinds of interest. Of course, we have strong interaction with the other divisions in an interdisciplinary way. So equally strong is our material science and technology division, where we deal with minerals, alloys and composites, ceramics, electronics, coatings, pigments, polymers, etc. And in the agro-processing unit, we work on post-harvest processing, oils and spices, functional food, healthcare, nutraceuticals, and value addition of agri products. We have a microbial process and technology where the strength is on fermentations, enzymes, mainly industrial enzymes, biofuels, and biochemicals. And then we work on environmental technology because, while we do a lot of research and developmental activities, it is also equally important that we should take care of the environment. So we have a strong environmental monitoring, activity in the form of waste management, both solid and liquid waste management, odor control, environmental impact assessment, etc. So this is a general view of the institute. At the institute, I currently lead the institute as its director, but I at the same time actively involved in my own research areas, where I focus on certain aspects of soft materials. So my research group is mainly interested in supramolecular chemistry, molecular self-assembly, so on and so forth. So my group is, my students very fondly call me AG. So you will see on the left-hand top, AG 5832. 58 indicate my age, and 32 is my active, independent years of research. Okay, in my group, we mainly focus on pi systems, and most of you chemists know what are pi systems. They are the, integral part of many electronic devices, and they are widely used in many different applications. For example, functional dyes and colored materials. And we are interested in pi systems, and we use pi systems as building blocks for creating supramolecular architectures through molecular self-assembly, making use of weak non-covalent interactions such as hydrogen bonding, pi stacking, electrostatic interactions, van der Waals interaction, etc. We create soft materials, for example, organogels. We create similar responsive materials. We are also interested using pi systems as molecular probes, especially fluorescent pi systems, for sensor applications and imaging and diagnostic applications. And recently, we got interested in coordination polymers and covalent organic frameworks. And in the literature, probably you can see some of these activities of our research group in the form of reviews and accounts, etc. And you will also see a large number of our publications on this particular topic, that is on supramolecular architectures, their shape, their size, and their properties. So these are from our contribution from our research group, where we use pi-extended system as active building blocks to create a variety of aesthetically appealing supramolecular architectures. You can see many different kinds of architectures here. So for example, you can see vesicles, you can see tubes, you can see fibers, you can see helices, toroids, honeycombs, so on and so forth. So you can name any such architectures, and using the principles of chemical synthesis, and then using the principles of covalent and non-covalent chemistry, weak interactions, you can now articulate how to create different kinds of supramolecular architectures of different size and shape, and then you can investigate how these structures, their size and shape, influences upon their physical properties, and then you can manipulate their physical properties, or you can fine-tune these physical properties by manipulating the structure and shape of these supramolecular architectures. Since the audience may have interest in various different areas of supramolecular chemistry, soft materials, or otherwise, I'll just show a few selected recent publications from our research group to give you a flavor of what kind of recent research that we are doing. So in the field of supramolecular chemistry, we make these architectures, we study their size, their shape, and their properties. And we are also interested in creating aesthetically appealing supramolecular architectures. For example, superhelices, one of the most intriguing structures that you can see in nature. Many different kinds of superhelices available. You can see in nature. But on using artificial or synthetic molecular system, how to create such superhelices, and what kind of properties that you can derive from these superhelices. So one of our recent example, which is shown over here, which we published a few, in 2017 in Engavande Chemie, where using these kind of extended pi systems, we can create these kind of superhelices that you see in the transmission electron microscope and atomic force microscope. One of the interesting thing is that you will see very, very high circular dichroism effect, or cotton effect on these super helical structures, and we have done a significant amount of research to find out how these are formed, and how you get such very high intensity of circular dichroism, etc. We also work on our recent interest. I mentioned that we work on coordination polymers and covalent organic frameworks. So we use some of these fundamental chemistry to create interesting supramolecular architectures. Say, for example, lotus leaf, rose petal effect, etc., which are super hydrophobic materials having different kinds of properties. So we use some of these recent chemistry to create or to do surface modifications of known materials to impart some of these properties as you see here. This is another recent example. A couple of years back, we published in Nature Communications on stepwise control of host-guest interactions using coordination polymers gel. We make some coordination polymers, as you can see here in the TM image, and you can functionalize these coordination polymers with some functional group, and then you can make host-guest complex on the surface of this, and then you can use temperature as a stimulus for the selective release of the guest molecules from the host. We also have quite a bit of interest in coordination polymer gel and covalent organic frameworks. So this is one of our recent example on a new kind of covalent organic framework, which can be used for the detection of selective detection of double-stranded DNA. And then just this year, we published another paper on similar topic, but this is on use of surface charge regulation and exfoliation of covalent organic framework for controlled killing of bacteria on the surfaces. So with this brief general overview of some of our activities, I would now like to invite your attention to the topic which I have promised to talk today, that is on stimuli responsive self-assembly. So when we talk about stimuli responsive soft materials, we know different kinds of stimulus that we use or chemists use for controlling the overall physical properties of materials, soft materials or polymers. And these different stimuli can be, thermoresponsive materials, temperature, which is imparting a kind of thermoresponsive properties. Or you can use light as a stimulus for creating photoresponsive materials. You can use voltage for electroresponsive activities. You can use mechanical stress or pressure for creating mechanoresponsive materials. So you can use all these kind of various stimuli to control the properties. For example, you can control the shape and many electronic properties of these materials using one of these different stimuli. I'll give you a few examples from our own research on some of these stimuli responsive materials. Say, for example, thermochromic materials or thermochromic self-assembly. Several years ago, we published a paper in JACS on an organic gelator which is thermally responsive in terms of its fluorescence. So what you see here is a paraphenylene vinylene based gelator, which is one of our favorite molecules, where we have done significant amount of research to understand their properties. You will see a series of publications in the literature on these particular molecules, this short paraphenylene vinylene that you see here. In this particular work, we have shown that the fluorescence can be significantly modulated using temperature as a stimulus, and you can use for thermal recording or thermal writing on these kind of materials, which can be reversibly controlled. So what you see here in the left-hand side is a film prepared using this kind of hybrid gelator of polystyrene and OPV. And on the right-hand side, you see something written over it using a thermal stimulus. And once you expose this to solvent, you can erase it, and then you can use it a large number of times. So this is one example for a thermoresponsive material. I'll show another example for a mechanoresponsive self-assembly, This is one of our recent papers on ODP, that is difluoroboradiazine derivatives, which is widely known and popular dye in the literature for used for various applications. And we have designed molecules which undergo self-assembly. And this self-assembly will lead to soft materials and organogels, where you can significantly modulate their emission using mechanical response. And by doing so, when you apply shear or a pressure on this, you will see the fluorescence significantly changes. So this is the initial fluorescence, as you see, as the material, and this is the fluorescence of the building block, that is a starting material. This is a self-assembly, and this is after shearing. And an interesting thing is the very broad emission spectrum that you see, where you have a strong emission coming up the near infrared region. And the intensity of this can be significantly improved by applying a pressure on this. And there are not so many molecules or assembly you can find in the literature which strongly emit in the NIR region. So here is one example where you can create strong NIR emission upon mechanical stress. This is another soft materials, again based on paraphenylene vinylene systems. By applying pressure on a film or this material, you can write something, or you can completely change their emission color. This is another example on another system that is photochromic, which is probably one of the most favorite for material chemists, because photochromic systems have a lot of applications. And light is one of the most sensitive stimulus that you can very precisely use for controlling properties. And I'll show you one very popular reaction, which is a standard textbook chemistry, which is the cis-trans isomerization of acebenzene. And most of the students sitting in this audience probably are familiar with this kind of photochemistry, which is known as cis-trans isomerization of acebenzene. Under normal condition, you have the trans isomer, trans isobenzene, and once you irradiate it with UV, you get, UV or visible light, you get the isomerized product, which is cis acebenzene. And when you expose it to thermal, or when you irradiate with UV light, then you will see the cis going back to the trans. But doing so, you can now induce a lot of changes in the properties. When you look at from the single molecule level, probably the changes may not be that significant. But you can note here that once the trans having a length of roughly 9 angstrom goes to the cis, the length will significantly reduce to 5 angstrom. But this means that there is a size reduction. So when you look at the single molecule level, this size reduction may not be that big. But if you imagine a large material having a large number of such molecules, then you can bring some collective influence on the overall properties, for example, size. So when you reduce the length of the molecules, in a bulk material, you can even reduce the bulk size of the material. So that means a shrinkage of the materials. And this can cause some change in the shape, and then you can create shape memory materials. And you can also note that the dipole moment of the molecule significantly changes when this isomerization happens. For example, the trans has less dipole moment, and when it goes to the cis, the dipole moment significantly increases. This can also bring in a lot of changes to the properties. And this isomerization has been widely used in polymer, making different kinds of elastomers and other kinds of polymers, which can change their shape upon excitation or irradiation. Our interest in this was in combination with molecular self-assembly. So what I'm showing here is one of our previous publications, which we published in 2012 in Journal of American Chemical Society, where we have designed some special or tailor-made isobenzene derivatives, and then we have integrated this with some self-assembling motifs, and then induce their self-assembly as a function of the cis-trans isomerizations. You can see that the trans one will initially form this kind of nanodots, as you can see here in the top left-hand side of the image shown over here. These are small nanodots of the trans derivatives, but once you irradiate, you immediately see there is a morphology change happening, and the nanodots are now converting to nanorods. And you can see that they are more or less well-defined nanorods, and with time, the size of the nanorods, or with irradiation time, with increased irradiation time, you will see that the size of the nanorods are increasing, and from the nanorods it go to something like a microrods, where a few micrometers in length. But you see the width is more or less uniform throughout the length of the rods. And now, once again, when you irradiate and the cis goes back to the trans, you will see you can disintegrate the entire, induce the disintegration of the rods, and you can get back the nanodots. And this is a reversible process. You can repeat this any number of times. Here is another example where we have demonstrated how cis-trans isomerization can be used to control the helicity of supramolecular helical architectures. So here you see extended pi systems on the end of which we have connected to isobenzene moiety, which can undergo cis-trans isomerizations. And you can create different kinds of self-assembly using these systems. Initially, it forms a helical assembly depending upon the chiral handle that you have in the molecules. For example, you can create a right-handed assembly or left-handed assembly depending upon the chirality of the side chains that you have in these molecules. So what is more interesting is that when you irradiate these systems, so there can be some photoisomerization happening at the end of these molecules. It can be partial photoisomerization, so you create a mixture of both cis-trans isomers in the system. But once you create the cis isomer, you will be significantly changing the polarity of the system and also the size of the molecules, which seriously influence upon the self-assembly. So the initial helical assembly, if you take and then depolymerize it back to the monomers and do an irradiation so that some of these monomers undergo cis-trans isomerizations, and then if you cool it back, you create the self-assembly again, but you will see that the handedness of the assembly will be reversed in the opposite directions. So in this way, you can use light as a stimulus to control the helicity of, and in fact, this has a lot of implications in some of the natural phenomena happening in the system, because you see there are many such helical assemblies which are formed. Most of them have a very specific helicity, and you see the extraterrestrial chemistry happening in the atmosphere, the influence of solar radiations, so many other radiations, and all may have significant influence. And there are a lot of studies happening to understand even the origin of life in terms of chirality and helical formation of helical architectures. Now you can see here, this is the TM and the AFM image of the self-assembly before and after irradiations. So the top left hand, you see the TM image of P helix, that is right-handed helix. And after irradiation, you see that all the helical fibers have opposite handedness, that is M helix, which is left-handed helix. And the bottom, you see the atomic force microscopic image, where before irradiation, it is right-handed, and after irradiation, it is left-handed. So you can use light as a tool to control the helicity on a supramolecular landscape. So this is a mechanism which is a bit complicated mechanism. I have to in fact explain so many things, but due to the limitation of the time, I skip these things and request those who are interested, please refer these publications which I have shown earlier. Now, the rest of my time, I will focus on one particular recent chemistry that we have done, which is again on photoresponsive materials. You see the title here, supramolecular gel phase control 4+2 Diels-Alder photocycloaddition for exciplex mediated white electroluminescence. See, this 4+2 or 2+2 Diels-Alder reaction is one of the standard textbook chemistry. Okay. Photocycloaddition, say for example, photocycloaddition of androgen. The master students sitting in the audience probably might have learned something about Diels-Alder photocycloadditions, dipolar cycloadditions, etc. And you may be probably aware of the photocycloaddition of androgen. Okay, the 9th position of androgen undergo 4+4 cycloaddition to get this dimer that you have seen here. In presence of, this is in the absence of oxygen, but in presence of oxygen, molecular oxygen get added on this and you get the oxygen added product, or in the if you have a dinophile, then you get the cycloadduct. But if the 9th position is substituted, probably this reaction will be hindered. Okay. And there are a lot of standard textbook explanation on why this 9th position of androgen is selectively undergoing this photocycloaddition, why the other positions are not very active. And you can explain this, using some of the fundamental chemistry known in the literature. For example, Clark's aromatic pi sextet rule. According to this rule, you can see that the androgen dimerization preferably happens at 9th positions because you create two pi sextet on both the side when the addition takes place on the 9th positions, and you create two aromatic benzene unit with less amount of energy on. So that is the driving force. And in the literature, if you look at, there are you will see some example for the extension of these kind of classical, photocycloadditions. One of the example, and very interesting, is the photocycloaddition of 9-phenyl ethinyl androgen that you can see here. And when you make these molecules and when you radiate this, there are different possibilities, as you can see here in this slide. You can either undergo 4+4 cycloaddition or 4+2 cycloadditions. And if it forms 4+4, then there are possibilities of two different products, the 4+4 syn product and the 4+4 anti products, as you can see here on the left-hand side. Suppose you do 4+2, then again you have the combination of two different products, 4+2 anti and 4+2 syn. So in principle, you end up with a mixture of all these products. So then comes the question, suppose you want to specifically create one isomer, can you do? Of course, the chemistry has developed in such a way that you can do it by creating the appropriate ambience or using the right energy or reaction conditions. You can shift the equilibrium, and then you can at least get one of the product in selective yield, or you can increase the yield of your anticipated product, or your required product, I should say. So subsequent to this, if you look at the literature, you will see some interesting example. One such example is published in Science in 2011. See, a very, very simple approach. So if you want to specifically create one of the isomer, then you have to create some confinement to the system. So you fix the molecule in such a way that the two androgen molecules come face to face, so that you can specifically lead the photocycloaddition to form 4+2 syn product. Okay. And you can also fix this monomer or the starting material on other surface, for example, gold nanoparticle surfaces on fixed length, and then you can selectively do this reaction. Okay. But we thought in a different way. A few years back, we decided to, because we have some experience and expertise in supramolecular chemistry, molecular self-assembly, We can synthesize tailor-made molecules. So we thought of using this classical textbook chemistry and see whether we can have some control using the principles of molecular self-assembly. And then we asked the question, can we use a gel medium as a confinement for selectively doing this photocycloaddition? Because gel chemistry is, even though it's a soft material, it's made up of molecular assembly. So you can create some kind of a restricted environment in a gel medium. And also it strongly depends upon the way the molecules are packed within this gel medium. So if you can achieve some sort of controlled assembly of the molecular system, then probably you can do selective chemistry. And this has been previously shown, for example, for doing energy transfer, electron transfer, etc., using gel as a confined medium. Some specific, isomers or polymorphs have been created using gel as the medium. So gel has been used. But whether we can use this technique for controlling this photochemistry. And if we can do this, then probably we may be able to use this material for some specific applications. So if you take this molecule, in principle, again, it can give these different kinds of isomers that you see here. Okay, so there are different possibilities, but out of these possibilities, whether you can get one or two in a selective manner, this is what we were interested. And interestingly, we found that this molecule self-assemble, and as a result of the self-assembly, it forms a soft material, it forms a gel medium. And we have characterized the gel medium using all available techniques. I'm just skipping it. This is the TEM image of that. This is the comparison of the spectral, properties in different solvents. And we found that when it forms the assembly, the two androgen moieties are packed in an offset manner. It doesn't come face to face as you see here. And we have established this kind of packing and assembly using various kind of analytical tools. And then we came to a conclusion that this is the way molecule pack in the gel state that you see in the left side. So you can see that the androgen of each molecule come face to face with the acetonic double bond of the triple bond of the other moiety, so that there is a possibility of a 4+2 addition, photocycloaddition between the androgen and the triple bond. And if this happens, then the assembly undergo, some kind of disturbance due to the conformational, characteristic of the photocycloaddict, and this can disturb the self-assembly. So the gel can go back to the soul, and that is what you see here. You take the gel. In the gel, the molecules are assembled in a specific fashion. When you irradiate, you will see that it goes back to the solution. And now you see the conformational changes also. Initially in the self-assembly, it is an extended tape-like morphology, which upon irradiation goes to some sort of granular kind of structures, indicating the disassembly process as a result of this photocycloaddition. And we have done various example NMR and XRD and many different kinds of experiment to establish the structure of the photocycloaddict and all other related characteristics. And this is a comparative photophysical properties or the spectral absorption, emission, and lifetime data of the monomer and the photoaddict. And you can see that the monomer has the red emission absorption that you see once the undergo photocycloaddition. There is a significant change in the absorption and the emission, and also the lifetime decay data. Now, see, this kind of photochemistry is known because of some fundamental importance. But if you look at the literature, you won't find any application for this kind of photochemistry. People are trying to use this photochemistry for application. So we also thought whether we can use this photochemistry, especially this controlled photocycloaddition, for some specific applications. Since we have some interest and we have some expertise in our institute, in our division, on various kinds of devices, organic electronic devices, for example, display devices like organic light emitting diodes, we thought of using these molecules to find out their utility in fabricating organic light emitting diodes. So we have used both the molecules, our starting molecules and also the photocycloadect as the active component to fabricate organic light emitting diodes, multi-layer devices using different kinds of electron and hole transporting materials. And now you can see, if you use the starting material, that is a starting compound, the building block, you get blue emitting organic light emitting diode using polyvinyl carbazole or some other electron transporting agent. But if you use the photoadect in place of the monomer, then interestingly and also surprisingly, we found that instead of blue emission, you get white light emissions. So in fact, this was hard to believe why this photoadect is giving white light emission. Whereas for white light emission, you need all the fundamental colors to be emitted by the system, the RGB, red, green, blue. The question is, where is this different, especially green and red coming? Because it is basically the material is emitting blue. So we had to do a lot of experiments to find out the actual mechanism and reason why we are getting white light emission. So here is the comparative electroluminescence, photoluminescence spectra of this molecule, that is the starting molecule before photoirradiation, using some carbazole derivatives as the electron transporting material. And you see, initially, this is the EL, the red one is the EL, electroluminescence, and the blue one is the PL. Okay. And in both cases, you get the same blue emitting. But interestingly, when you take the photoadect as the active material and use the same electron and hole transporting material, you see the PL, that is the photoluminescence, is similar to that starting compound. Okay. But if you look at the EL, you see EL is very, very different, significantly different. And you see a strong red emitting component and also a bit of green emitting component coming in. And now if you look at the electroluminescence spectrum covers the entire RGB region, blue, green, and red. As a consequence, you see the white light emission. And you can use different kinds of hole transporting and electron transporting materials to fabricate different kinds of organic light emitting devices or electrodes. Then in all the cases, you see when you use the photoadect, you get the white light emission. And if you use the starting material, you get the blue emission. And in the case of the photoadect, the PL spectrum is always like the spectrum of the starting material. So electroluminescence is the one which is making the difference. So now the question is why the electroluminescence gives such broad spectrum comprising of all the three fundamental emitting components, the red, green, and blue. So we found that in the literature, there is something called electroplex. Especially if you look at some of these electroluminescence, there is a phenomenon called the electroplex emission, electroplex formation. What is electroplex? This is a kind of exciplex, which you see in the case of photochemical reactions. When you excite a donor acceptor and it goes to the excited state, you form excited complex. It is called exciplex. And exciplex emitted the longer wavelength. Something similar to this, but this is not exciplex, this is called electroplex. So instead of light, if you use some potential, you apply some voltage, you can create a similar kind of a situation where there can be electron flowing from the host to the emitter, and it forms a kind of host emitter complex, just like an exciplex. But since this is an electroplex, when you excite the molecules photochemically, you don't see this emission. That is, you don't see the emission. But if you excite this system by applying a potential, then this complex is formed and you see the electroplex. That is, you see in the EL spectrum. And that is the reason why you see the red emission coming here. And you can see this is the energy coordinate plot. This is actually the photoadduct. The photoadduct in the excited state emits the blue light, as you can see from the PL. But when you apply potential, you see the photoadduct plus host electroplex, and the electroplex emit red emission. And also maybe some excited state complex may be also formed from the photoadduct or the starting material when there is unreacted starting material present in the system. So that can give a green emission. So in principle, what you see is a combination of all these fundamental colors, which is responsible for the white light emission. So this is, one specific and interesting, very recent example from our group. And you must remember that this is a very, very fundamental textbook chemistry. Now, using that old chemistry, we are trying to find out some new interesting applications in combination with the principles of molecular self-assembly and supramolecular chemistry. Now we are trying to use this for various other applications. Say, for example, whether we can create smart windows. Smart window is now coming in a big way, which can save energy, because all the windows, the indoor light and indoor heating is mainly due to the glass windows that we use, and in the broad spectrum solar radiation contains quite a bit of NIR and IR radiation, which is responsible for indoor heating. And because of this indoor heating, especially in a tropical region like ours, we have to use significant amount of electricity for cooling inside. So this will create a lot of environmental issues, and now people are trying to find out solutions how to mitigate these kind of issues. So we are now trying to find out some of these photochemistry and soft material chemistry to create smart windows. In fact, I have a video. I don't know whether I may be able to show this video, where I will try to see. I don't know whether you can see this video. Are you able to see this video?
Yes, sir. Yeah, we can see it.
A transparent material upon exposure to light is going to a translucent or an opaque. And by doing this, you can block the entry of light, and especially IR light. And then if you cool it, you can see that it is going back to the transparent. So this can have a temperature and light responsive smart windows. I cannot explain you everything about this because this is still under patenting, and we are still working out on a large scale fabrication of such kind of windows. Probably another occasion I may be able to show some of the applications of some of this fundamental chemistry along with the soft material science to make some of the interesting materials. So with this, I'm closing my lecture by thanking all my former students, associates and all. Particularly for this lecture, I would like to thank Dr. Magesh Srinivasan, Dr. Anish, Dr. Krishnan Karta, Dr. Sandeep, Dr. Rahul Dev Mukhopadhyaya, and Dr. Satyajit Das for their contribution. These are the people who were working on soft responsive materials. And finally, I thank all my international collaborators, particularly Dr. Yagi, who helped in some of these, white light emitting, fabrication of white light emitting, organic light emitting diodes. And finally, the financial support from funding agencies, my J.C. Bose fellowship from ACRB, and also the Council of Scientific and Industrial Research. Finally, I thank you all for your patient listening.
Thank you very much, Dr. Ajay Ghosh, for giving us time in your busy schedule. and sharing with us this information about this interesting chemistry you are doing. So I think we have maybe time for one question. If anybody has a question, so please raise your hand. Well, I'll pick from the list. I see Professor Padmanabhan. He's hello.
Is Professor
Professor
Padmanabhan?
Padmanabhan.
He may have to unmute his mic and then ask.
Am I audible now?
Yes, now you are
Okay.
audible.
Okay.
Yeah.
I said, as usual, your great talk about your wonderful work.
Thank you.
Just a few short questions about. I think it's Mahesh work. He talked about I saw that is cis trans isomerization, and then he talked about Oswald ripening, and
Yes.
and you have that long, the dot becoming a long crystal-like thing.
Yeah.
Is that the assembled one? Is this cis isomer or the same trans isomer?
The trans isomer is initially undergoing the assembly to form these dots, nanodots. And when you irradiate, the trans will go to cis. And once it goes to the cis, it forms the rod. Because, the polarity of these dots are increasing significantly due to the...
Okay, but then it goes back to the transform, right?
It goes back to the transform if you keep it under dark, or you again irradiate with UV light.
Oh, okay.
And then you can, then your nanorods undergo disassembly, and it comes back to the, nanodot if you cool the solution again.
Okay. And regarding the mechanotropic, the system, I think is a body pi, or am I right?
Yeah.
Or,
Yeah.
okay.
Yes.
So you talked about the fluorescence enhancement on applying the pressure. Actually.
Yes.
Is it because you somehow control or diminish or decrease the internal conversion, or shall I say the, for example, through vibrational relaxation? Is that the reason which?
Yeah, that may be happening because initially, actually, what is happening is that there is an initial packing. Yeah. This packing is not a very stable packing. It's like a metastable condition. So when you apply some stress in the system, then it goes to a more thermodynamically stable self-assembly.
Maybe you just control some of the vibrational modes actually under control, and then perhaps, I mean, I'm just guessing it actually. So you probably, I don't know whether you explored.
Yeah, probably you are right.
Okay,
and,
that's a very.
But now, see, when we first published this paper, we were actually not sure of what is the reason for such a broad emission in this system, because this is a very unusual kind of an emission.
I know, because it's really exciting.
See, for example, if you look at the stock shift, you can see the pseudo stock shift when you're considering the absorption and then this the faraway emission at the NIR. It is huge.
I'm going up to NIR. It's
very wide. Up to the NIR region, and this is very, very rare situation. So at that time, we were actually not fully aware of what is happening at the excited state. But now, subsequently, some of my other students are working on this, and now they have an explanation for this. So what is happening is that, which we will be publishing very soon in the process of writing the manuscript, what we found is there is something called a domino effect here. So there is an energy transfer process happening because the energy landscape of the self-assembly is very, very diverse, and the kind of supramolecular aggregates that you are forming is a diverse architecture in terms of its energy landscape. So when you excite it, there is a consecutive energy transfer happening in the system. Okay, and by applying a pressure, you are now modulating this.
Yeah. Okay.
But you are increasing the efficiency of that energy transfer.
So that.
So
thank you. Thank you so
much.
Okay,
sir.
Yeah, thank you so much.
Sorry to interrupt.
It's okay. I know. Short of time.
Yes, sir. Yes, sir. Okay, so we are running out of time. So maybe I request participants to post their questions if they have anything. We will make sure that the questions will reach Dr. Ajay Ghosh. So with this, let's all thank Dr. Ajay Ghosh.
people to write to me if you need any kind of clarification on any of these things, or you can read the literature, some of these publications.
Thank you, sir. Thank you very much. Okay. With this, now it's time for our next speaker. So we have Professor Swati RS from ISER Trivandrum. So I request Dr. Adira to give a brief introduction about Professor Swati.
Thank you, sir. Good morning, all. Is it audible?
Yes, ma'am. Yeah.
Okay. So good morning, all. It's my privilege to introduce one of the eminent women speakers of our conference, Dr. R.S. Swati. Since 2010, she has been working as Associate Professor at School of Chemistry, Indian Institute of Science, Education and Research, Trivandrum. She had received her PhD from Department of Inorganic and Physical Chemistry, Indian Institute of Science, Bangalore, and she is a well-established scientist in the area of theoretical chemistry. Her major research objective is to provide a fundamental understanding of various chemical systems and phenomena using the methods of theoretical chemistry. She is honored by more than 20 awards, which include Women Excellence Award by Department of Science and Technology, Science and Engineering Research Board, Government of India in 2017, Young Scientist Award of the International Science Academy, New Delhi in 2016, Young Scientist Award of the Kerala State Council for Science, Technology and Environment in 2015, Platinum Jubilee Young Scientist Award of the National Academy of Science, Allahabad in 2017, Distinguished Lectureship Award of the Japanese Chemical Society for the work on theoretical chemistry in the year 2015. She has numerous high-impact peer-reviewed international publications in her studies with a recognizable number of citations. She is one of the editorial advisory board member of ACS Applied Materials and Interfaces. Fortunately, today she is with us to deliver a speech on the topic Continuum and Atomistic Modeling of Carbon Nanostructures. On behalf of Organizing Committee, ICMSC 2020 and Department of Chemistry, Amrita Vishwavidyapeetham, I welcome you, ma'am, to the conference. It's your turn, ma'am. Welcome.
Professor Swati.
Ma'am?
Hello. Yes, I am there. Can you hear me?
Yes, we can hear you. If you can please upload the presentation.
Okay. Can you see the slides?
Yeah, ma'am. Slide.
Professor Swati, now we see it as the editable mode. If you can please put it on the, okay, yeah, now it is.
Is this fine?
Yes.
Okay. So at the outset, let me begin by thanking the organizers, Professor Naveen Kulkarni and others for having invited me for this meeting. I'm really glad to be presenting our research contributions here. Without taking much time, since we are already behind schedule, I would like to begin the talk. The talk is entitled Continuum and Atomistic Modeling of Carbon Nanostructures. So let me first give you a feel for how theoretical analysis of nanostructures is typically done. If you look at modeling of various chemical systems, what happens is at small molecule level, we typically employ quantum mechanical approaches to describe their properties. While at large scale level, for instance, supposing we want to treat proteins, Then we employ classical molecular dynamics. However, when it comes to nanostructures, it is always a compromise that one has to make, because in case of nanostructures, the system sizes are such that the microscopic models are not efficient enough, while the macroscopic models are not accurate enough. And therefore, there is a compromise that one makes and says that, okay, we will employ multi-scale modeling and computation for describing the nanostructures. Now, there is an urgent need to develop fast and efficient modeling protocols without compromising too much on the accuracy. Because typically what we would like to do is we would like to calculate the properties of nanostructures at reasonably acceptable time scales without compromising on the accuracy. And there are a lot of protocols that are currently being developed to describe nanostructures along these lines. Our group at ICER Thiruvananthapuram has been interested in multi-scale modeling and computation of nanostructures. Typically, there are two classes of nanostructures that we focus on. One is plasmonic nanostructures and the other is carbon nanostructures. So what do we look at in carbon nanostructures? We look at carbon nanostructures for sensing, separation and storage applications. So what we typically do is we design materials that can be used for sensing, separation and storage applications. And what are the tools that we employ here in our studies? We employ multi-scale modeling approaches. Sometimes we resort to quantum mechanical approaches. Sometimes we employ very, very classical kind of approaches. And I will describe some of these as we go along in the talk. And the kind of systems that we look at typically are systems such as two-dimensional substrates like graphene, graphines, graphene nanomeshes, and so on. We also look at one-dimensional substrates such as carbon nanotubes. We do also work with fullerenes. So our research in some sense encompasses all aspects of carbon nanostructures. Just to give you a feel for what we are also interested in from the plasmonics perspective, we are a group that is interested in calculating optical features in metal nanostructures. Now, why are they interesting? Because it has been established for quite some time now that plasmonic nanostructures are extremely useful for surface enhanced spectroscopy kind of applications. Now, when we say surface enhanced spectroscopy, what happens is that when metal interacts with light, there are these collective electronic excitations that get excited. And once these are excited in the vicinity of the nanostructures, there is a huge enhanced electric field that is formed. And this could be typically used to enhance optical cross sections of molecules that can be bound in those regions. So one of our major goals in the research group has been to look at plasmonic nanostructures. But this is a story that I will reserve for another day. And today's focus will be on the carbon nanostructures aspect. So let me begin with giving you a feel for how modeling of these carbon nanostructures is done. First, we follow a series of hierarchical approaches, one of which is approximate continuum based approaches. All right. And then a slightly higher level of sophistication is brought in by looking at semi-empirical atomistic approaches. And of course, the best in the business that you would want to think of is accurate quantum mechanical approaches. And as I have already told you, most often for a lot of nanostructures, accurate quantum mechanical approaches are computationally prohibitive. And therefore, there is a lot of emphasis on developing semi-empirical and approximate continuum approaches for modeling carbon nanostructures. Of course, one has to make a judicious choice of the approach for a given system by considering the problem in hand. Okay. To give you a feel for the evolution in carbon chemistry, we typically had for several decades two conventional allotropes of carbon, graphite and diamond. Subsequently, we had the discovery of fullerenes, carbon nanotubes and graphene. All right. Now, in this series, there are a latest entrants. The system is referred to as graphines, and these are what we refer to as new members in carbon flatland. Okay, why do I say flatland? Because these are two-dimensional materials, and typically these are formed from sp and sp2 hybridized carbon atoms. And as you can see, there are a variety of these carbon networks referred as alpha, beta, gamma, delta, rhombic forms of graphines. And each of them is characterized by a specific porous architecture that is extremely useful for sensing and separation applications. Okay, so if we look at these 2D materials, one of the major issues with graphene based materials is that typically one has to drill pores through the carbon network if one has to use them for sensing and separation applications. However, with graphenes, what is possible is that you can kind of do a bottom-up synthesis of these porous architectures with controlled porosities. And therefore, it gives you a kind of series of flexible pores that you can use for sensing and separation, which is why in the last 2 to 3 years, the research on graphenes has really taken off. Okay, just to give you a feel, for some applications, graphenes have already been proposed to be extremely useful for energy storage applications, for catalysis, for water desalination, and for some important chemical reactions. What I have told you so far is that we have a series of carbon nanostructures. Under one class, we could say that we have graphene, carbon nanotubes, and fullerene. On the other hand, we could say that we have graphenes, which have interesting porous architectures, and we have graphene nano meshes. Again, the mesh architecture is extremely important for its function. All right. So now the question is, how do you model these two classes of carbon materials? Now, as you can see, I have already divided them into two kinds of classes. One is graphene, carbon nanotubes, and fullerenes, while the other is graphenes and graphene nanomeshes. Now, why did I make them into two classes? Essentially because these systems, which are on the left-hand side, graphene, carbon nanotubes, and fullerene, they are extremely symmetrical structures, and this symmetry enables adopting continuum approaches to describe their properties. I will talk about continuum approaches as I go along in the talk. So typically what happens is, if you think of graphene, you could see that you can approximately represent it as a sheet of uniformly distributed carbon atoms restricted to a plane. Okay, and the dimensions of the plane you can decide depending on the size of your graphene ribbon that you are interested in. On similar lines, if you look at carbon nanotubes, you could say that carbon nanotubes are essentially rolled up sheets of graphene, of course, but then there's one-dimensional cylindrical structures, effectively one-dimensional cylindrical structures. And typically you could represent them as uniform density of carbon atoms confined to move on the surface of a cylinder of a given radius, let's say B, as indicated here. Same is the case with fullerene. Fullerene is typically a spherical kind of molecule, and therefore you could say that the carbon atoms are uniformly distributed on the surface of a sphere with radius B again. Okay, so this enables us to evaluate a lot of integrals that come up in the mathematical description of these materials, and it simplifies the analysis. Okay, so continuum modeling is extremely powerful because it essentially exploits the symmetry of these carbon nanostructures. However, if you come to the systems that are shown on the right hand side, you will immediately realize that there is some important features that we would want to capture very accurately, which is nothing but the porous architecture here. Okay, for example, for any separation function of a graphene nanomesh, what is extremely important is the porous architecture that you see out here. Okay, now that means that any model that you would want to describe it with has to accurately capture this pore architecture. Okay, same is the case with all forms of graphenes, because for any of its function, its porous nature is extremely important. So here we do not really resort to continuum modeling, because continuum modeling kind of washes out the porous architecture, and therefore we adopt what are known as atomistic approaches. Okay, the atomistic approaches essentially take into account the pore configurations accurately. Okay, whether you use atomistic or continuum approaches, one of the key objectives here for theorists is to design a set of transferable model parameters, okay, which you could seamlessly adapt to describe phenomena on a variety of such systems. Okay, so one of the current day challenges is actually to be able to design transferable model parameters for these carbon nanostructures that one could use across a range of systems and describe the chemical properties, hopefully at reasonable computational costs. So there are three kinds of frameworks that we often employ for modeling intermolecular interactions involving carbon nanostructures. The first is what we refer to as a continuum model. The second is the discrete continuum model, while the third is the discrete model. I will talk about each of them now. So in continuum model, what happens is that we have two carbon nanostructures, both of which could be described using a continuum approach. What does it mean? It means that both the systems possess the symmetry such that you can resort to continuum modeling. For example, if we want to model a fullerene encapsulating into a carbon nanotube, fullerene could be treated as a spherical system with a uniform density of carbon atoms. A carbon nanotube again can be described as a cylindrical system with a uniform density of carbon atoms. All right. So now there are only a specific number of cases where such continuum modeling is possible. So sometimes, for example, we would like to model, let's say, a drug molecule that is getting encapsulated into a carbon nanotube. Okay, let's say a cisplatin molecule getting encapsulated into a carbon nanotube. What do? We obviously cannot model a cisplatin molecule using a continuum model because it just doesn't possess the symmetry that is required for a continuum model. Okay, and therefore what we say is that we treat the cisplatin molecule as a discrete model within the purview of a discrete model, and the carbon nanotube within the purview of a continuum model. So what we say is that the cisplatin molecule, for instance, comprises of a collection of atoms which are represented as pink balls here. Okay, and each of these atoms would interact with tiny element on a carbon nanotube, and you eventually integrate over all such tiny elements on the carbon nanotube. Okay, so let me now go back to the continuum picture and describe what we do. So we have a tiny element ds1 on the first nanostructure, ds2 on the second nanostructure, and both of these are separated by a distance rho. The potential of interaction between these two entities is what we denote as V of rho. All right. Then what we do is we have two such tiny elements, ds1 and ds2, and if we integrate over entire surface of first system, we get the contributions from all the regions of the first system. If we integrate over ds2, we get the contributions from the entire surface of second system. Okay, so basically we have two sets of integrals, one over the first nanostructure, the second over the second nanostructure. And the two quantities eta1 and eta2 that you see out here are nothing but parameters that characterize the uniform density of carbon atoms on these two substrates. All right. So within a continuum model description, what is the total interaction energy between two such carbon nanostructures? It is essentially given by such double integral. All right. So in contrast, if you look at a discrete continuum model, for example, as I told you, in the case of a cisplatin molecule getting encapsulated into a carbon nanostructure. So you consider the interaction of one of the carbon atoms here, one of the atoms of cisplatin here with a tiny surface element of the carbon nanotube. And if this separation is rho of I, we have V of rho of I. And now we have to integrate over one surface element, which is ds here, which means when you integrate over entire ds, you will essentially take into account the contributions of interaction of the ith atom with the entire carbon nanotube. And this process, of course, has to be repeated over all the atoms of the cisplatin molecules, which is described by the summation over I here. All right. And you see one parameter eta here, which is essentially the atomic surface density of the carbon nanostructure here. Okay. So the total interaction energy between, let's say, a discrete atomic structure and a continuum system is what is given by this relation. So we sum over the contributions of all the atoms and we sum over the contributions of all the tiny elements in the carbon nanotube. Now the third model that we use for a description is what is known as a discrete model, which mainly is used in situations where both the interacting systems are not amenable to continuum modeling. Okay, suppose we would like to describe interactions between two cisplatin molecules. Both of them do not have the symmetry that is required for a continuum description. And therefore, what we do is we consider an ith atom here on one molecule, jth atom here on the second molecule. If the separation between them is rho ij, the potential energy of interaction between them is V of rho ij. And eventually, to get the total interaction energy, we will have to sum over contributions from all the atoms in the first molecule and all the atoms in the second molecule, which is indicated by a double sum here, sum over I and sum over j. Okay. So broadly speaking, in order to describe interactions between carbon nanostructures, typically we employ modeling methodologies ranging from a continuum model to a discrete model via a kind of discrete continuum description, wherein you can choose to have a mix of both continuum and discrete formalisms. Okay, so now here the problem that I would like to talk to you about today in such continuum modeling description is the phenomena of adsorption and encapsulation involving graphene and carbon nanotubes. So here, as a first example, I would talk about noble gas atoms binding on graphene and encapsulating into carbon nanotubes. Typically, when we talk about encapsulation into carbon nanotubes, we talk about two kinds of modes of binding. One is the endohedral binding, the other is the exohedral binding. Okay, so the endohedral binding is what is referred to for the encapsulation within the hollow interiors of carbon nanotubes, while exohedral binding is what we call for the binding of the atoms on the exterior surface of the carbon nanotubes. Okay, so these are illustrative systems that I would talk about as I go along. I would also focus on a specific class of carbon clusters, which are referred to as monocyclic carbon rings. I would also tell you why they are important and so on as I go along. So let me begin with a very simplistic approach for modeling adsorption on graphene. Okay, graphene, as I have already told you, you could say that it is a continuum structure which could be described by both a ring model and a sheet model. Okay, what is a ring model? A ring model is what I would illustrate to you by this example. All of us know that one of the best examples of a molecular system that could be thought of as a building block for graphene is what is known as circumcoronene. All right, so here you see a structure of circumcoronene, which is C24H12. Okay, so this could be used as a smallest model system to represent graphene. All right, so now in continuum modeling, what we say is that such circumcoronene could be thought of as being consisting of a set of circular rings. Okay, and the rings are denoted here. The first set of 6 carbon atoms could be comprising one ring. The next set of carbon atoms could be comprising the second ring. The third set could be comprising the third ring. All right, and eventually what we have is hydrogen atoms in the outermost ring of the system. So basically what we say is that graphene is modeled as a set of rings, and what are these rings being how are these rings characterized? They are characterized by uniform density of carbon atoms. Okay, all that you need to do is you calculate the total number of atoms, divide by the circumference of the ring. That many number of atoms are there per unit length. Okay, this is the kind of representation that we employ in such kind of modeling. So let me just illustrate to you how we calculate the interaction energies here. Let's say I have a noble gas atom and I would like to describe the interaction with each of the rings here. Because eventually what I do is I consider one of the noble gas atoms, consider an interaction with one ring, and eventually sum over contributions from all such rings to get the total interaction with graphene. Okay, that is the kind of procedure that we adopt here. Okay, so now if we take one noble gas atom and one tiny element on the ring, you could say that these two are interacting via a Lennard-Jones kind of potential. Okay, the form of the Lennard-Jones potential is what is shown here. It has an attractive contribution which is given by minus 1 over R6. And it also has a repulsive contribution which is given by 1 over R power 12. Okay, and as I have already talked to you about, eta is the uniform density of carbon atoms, and Rn of course is the radius of the carbon ring or the hydrogen ring, depending on which ring we are looking at. So the advantage of writing the interaction energy using such integral representation is that we can actually evaluate the integrals explicitly, and we can write the interaction energy as a function of the distance z. Okay, this is extremely remarkable because once we have a closed form analytic expression, it is extremely easy to evaluate the distance dependence of the interaction energies. All right, now supposing on the contrary, you would like to do this analysis by using, let's say, an ab initio approach. Okay, what you will have to typically do is you will have to consider a molecular model system for circumcoronene as we have shown here, and you will have to consider performing electronic structure calculations with noble gas atoms placed at varying distances, and you will have to get the energy profile. Okay, and using ab initio calculations, typically it takes at least a few hours to do these calculations. But on the contrary, if you use a continuum modeling picture, you can actually calculate the interaction energies and the variation with distance once you have the formalism set in a matter of few seconds. Of course, I would like to caution here a bit by saying that these continuum approaches are approximate approaches, and their accuracy is not as good as the accuracy from an electronic structure calculation, for instance. But then these calculations are extremely insightful in the sense that you can arrive at a lot of important properties such as equilibrium configurations and binding energies, etc., from such an approach, and possibly use those as initial geometries for high-level electronic structure calculations, not compromising on the accuracy of the calculation. All right, so this is the philosophy with which we work with the continuum modeling picture. I would also briefly describe now a sheet model kind of description. So typically when we say a sheet model, it is a graphene is modeled as a rectangular or a square sheet. In this particular case, it is a square sheet, and the length of the sheet is 2L, and the width of the sheet is also 2L. Okay. Now, what is the difference between these two approaches? The difference is this. Earlier, in the case of a ring model, we had one set of integrals to be solved. But now when we use a sheet model, we have two sets of integrals to be solved. But then each one has its own advantages and disadvantages. Eventually, both models could be used to calculate the properties within a few seconds. All right. Now, if you notice here, I have also described in each case the results for a boron nitride sheet as well. All that will vary as you go from carbon system to a boron nitride system is that you will have a pair of additional A and B parameters, which are the Lennard-Jones parameters coming in. Okay, if you notice on this side, on the left hand side, you will see there is one set of parameters A and B. Okay, these are coming from the contributions from carbon atoms. While if you see here in case of boron nitride, you will have two pairs of them, one for the boron atoms and one set for the nitrogen atoms. But in any case, the calculations can be easily implemented for both graphene and boron nitride. And please also note here that these integrals actually can be evaluated, and the results are typically described in terms of what are known as Appel's hypergeometric functions. Okay, these are special functions, but then today it is easy to kind of employ them for calculations. Okay. Now I would like to give you a feel for how continuum approximations will contrast with the case of atomistic calculations. All right. So supposing I would like to describe the same system using an atomistic description rather than a continuum description. Okay, so I have a noble gas atom binding on top of a graphene sheet. What happens in a continuum description is that you can write point-point interaction between a tiny surface element on the graphene and a noble gas atom as indicated here, V of R. And what we have to do is we have to sum over contributions from all such tiny surface elements, which mathematically is nothing but the integral over the surface area of the sheet. Okay. In contrast, if we have a graphene model, what we do is that we have a noble gas atom and we have a set of atoms with possessing carbon and hydrogen for describing the graphene model. Okay, this is slightly larger than circumcoronene that we talked about earlier. And what we consider is, we consider one of the atoms in the carbon framework and consider its interaction with a noble gas atom, which is denoted as Vrij, V of rho ij. And what we eventually do is we sum over all such pairs of interactions between all the atoms of the sheet and the noble gas atom. All right, so this is basically what is known as a discrete sum over all such pairs of particles. Okay, this is the expression that you see here is a somewhat more generic one than what I have shown here, because this is for the case of one noble gas atom interacting with graphene, while the double sum here means that you can have several noble gas atoms interacting with all atoms of graphene system. All right. So this is the difference with regard to evaluating the interaction energies using continuum and atomistic calculations. Now the potential that I have shown you in the previous instance, which is the Lennard-Jones potential as you see here. Okay. This Lennard-Jones potential is what we use to describe pairwise interactions between various systems. For example, a noble gas atom and a tiny surface element is described by a pairwise interaction of this kind. Okay, but as you can see, this is a very approximate description. The Lennard-Jones potential has been used for several decades by theorists. But if you would like to describe the phenomena a bit more accurately, you will have to describe them using potentials that are much more accurate than the Lennard-Jones potential. And a lot of current research in the last 10 years has been directed towards developing accurate atomistic model potentials for these systems. Okay, the reason is simple. As I have already told you, continuum models can be very easily implemented in calculations. And therefore, if you have a potential that is much more accurate than the Lennard-Jones potential, you can perhaps improve the energetics very easily, okay, than what is possible from, let's say, first principles calculations. So this quest for atomistic potentials has actually led us to an interesting potential called the pairwise potential model, which has the attractive as well as repulsive contributions described much more accurately using anisotropic terms. Okay, I would not spend a lot of time on it because the potential itself is a bit more complex. As you can see, there is a dispersive term, there is a quadruple dipole dispersive and a quadruple dispersive term. There are anisotropic functions, and typically you have a tangent-Tonies damping function into the description. So today it is possible to employ such accurate potentials and perform calculations involving phenomena such as adsorption and encapsulation. Okay, here is just a glimpse of what we have been able to achieve by using test calculations on noble gas systems. So these are the curves that you see out here are from the DFT, which is basically more accurate than the modeling picture that I have been talking about all along. If we have a Lennard-Jones potential with very good set of parameters to describe the interactions, we have these dotted lines as the result. All right. But if we have a pairwise potential model description, which is much more accurate than a Lennard-Jones potential, you see the excellent fitting that you get for the DFT data. Okay. And just to give you a feel for how these calculations have to be tested, we have to basically perform these calculations, develop sets of model potential parameters, for example, in this case, the ppm parameters, and see if they are actually transferable to a range of chemical systems of interest. For example, in this case, once we develop a set of model potential parameters for the ppm model, we will have to show that they are actually transferable across a variety of systems. Okay, so for a large set of graphene nanoribbons, we have tested these potential parameters and shown that they are indeed reasonably accurate for describing noble gas adsorption on graphene. Okay, I'm now going to switch gears to another interesting system that has been of great interest to us, referred to as carbon nanotubes. And as you can see, carbon nanotubes are essentially rolled up sheets of graphene. Okay, mathematically speaking, how do you describe them? You have two real lattice vectors in the graphene framework, A1 and A2. And the way you fold the graphene sheet to form a carbon nanotube is what characterizes the two indices N and M. These are what are referred to as chiral indices. And the radius of the tube that is being formed is typically related to the two chiral indices N and M. Okay. And once you have a carbon nanotube, it is a cylindrical structure with a lot of empty spaces in between. And because you are able to experimentally control the sizes of the carbon nanotubes in terms of the diameters, etc., you can actually have precisely defined nanometer sized pores, which are extremely useful for storage applications. Okay, so as a first step, we have tried out the continuum modeling approach for encapsulation of noble gas atoms into carbon nanotubes. By now, I have established the philosophy of the continuum modeling approach, and therefore what we do here should be pretty obvious. We have a noble gas atom, we have a tiny surface area element on the cylinder, we write a pairwise potential between the interaction of these two entities, and then we have to integrate over the entire cylindrical surface. Okay, this enables us to get closed form analytic expressions for the interaction energies, from which a lot of useful properties can be calculated. So here is a summary of some of our results showing the variation of what are known as acceptance and suction energies as a function of the carbon nanotube radius. Okay, so what we do is that we ask this question as to supposing we have a gas atom entering into a carbon nanotube. Depending on what the radius or the diameter of the carbon nanotube is, the gas particle may be allowed, may not be allowed. Okay, what are the conditions under which it will not be allowed? If there is an energy barrier for it to permeate through, obviously the particle doesn't get allowed into the system. And therefore, it suggests that there must be an acceptance condition, meaning that there should be certain energetic conditions under which the particle can be encapsulated into the carbon nanotube. If the acceptance condition is not met, the particle is going to be rejected by the carbon nanotube. Okay. On the other hand, if the energetics are favorable, the total work done in bringing the gas particle from, let's say, -infinity to within the carbon nanotube, this work done has to be very, very high. Okay, under such conditions, mathematically we get this to be related to suction energy, and the maxima in the suction energy is what gives us the optimal nanotube radius that is extremely useful for encapsulating a given gas atom. So based on such energetics analysis using continuum modeling, we have been able to propose a series of optimal nanotube radii that are ideal for encapsulation of each of the noble gas atoms. Okay, as I have already stated earlier, we could do the analysis with more accurate pairwise potential model. And of course, this is much more involved than the simple Lennard-Jones kind of approach. And in fact, we have done DFT calculations and we have tried to fit the data from ppm model to the DFT data. And this enabled us to actually come up with a set of parameters for the ppm model, which can reasonably accurately describe the energetics of noble gas species encapsulating into a range of carbon nanotubes. And this methodology was proposed by us for the first time using the ppm description. Okay. So now I am kind of moving on to another problem, which is again extremely important as far as carbon chemistry is concerned. We are looking at carbon cluster adsorption and encapsulation into carbon nanotubes. So what are the carbon clusters? Why are they important? Carbon clusters are extremely tiny species that are of great interest to astrophysicists and molecular spectroscopists. The reason is simple, they are highly reactive and very difficult to prepare in the laboratory. So typically gas phase spectroscopy experiments have actually detected these carbon clusters. Okay, and we are here talking about a very specific class of carbon clusters which are referred to as carbon rings, monocyclic carbon rings, and you can see the geometry here. Okay, so these monocyclic carbon rings were very recently prepared. I will come back to this in a minute. Let me first describe the geometries of these carbon rings. The geometries of these carbon rings are indicated here. They are typically circular, monocyclic, and depending on whether they are 10 carbon systems, 14 carbon systems, 18 carbon system, 12 carbon system, 16 carbon system, and so on, you have them under either 4n plus 2 pi electron count rule or 4n pi electron count rule. And therefore, depending on this, you can have either a cumulinic geometry or a polyacetylenic geometry. But depending on the cluster that you have in mind, whether the cluster is going to adopt a cumulinic or a polyacetylenic configuration is of great debate today. Because what happens is that when you have these monocyclic carbon rings, the cumulinic and polyacetylenic geometries are found to be extremely close lying in potential energy surface. Okay, which means that it is very difficult to point out and say whether the geometry is indeed cumulinic or polyacetylenic. And the final word has to be given by experimental observations in this regard. So the first problem that we have talked about is a carbon ring getting adsorbed on a graphene sheet, and a carbon ring. The next problem is a carbon ring getting encapsulated into a carbon nanotube. Now there are two reasons why we were interested in looking at this. As I have already told, carbon rings are extremely reactive, and there has been a lot of effort to actually prepare them in the laboratory. So what we did was, we modeled the energetics of adsorption of carbon rings and encapsulation into carbon nanotubes, and suggested that these could be useful strategies for experimentalists to look at. All right. So we have again adopted the continuum modeling description. Again, by now it is all familiar to you. We have a monocyclic carbon ring with uniform density of atoms, and we have a square graphene sheet with uniform density of carbon atoms. On the contrary, in the case of single wall carbon nanotubes, we have a circular ring getting encapsulated into a cylinder, which is possessing a radius of B units. And the ring could be thought of as possessing a radius of A units. All that we need to do is, in the continuum description, we will have to consider a pairwise interaction, which is here given by the Lennard-Jones potential. We will have to sum over contributions from all the elements of the ring and all the elements of the sheet or the nanotube. Okay, and in this case, it is almost impossible to go beyond a Lennard-Jones kind of description, because all the integrals that we need to evaluate to arrive at the interaction energies are already complex with the Lennard-Jones potential. So it is almost impossible to go to, let's say, the pairwise potential model that we talked about earlier. Okay. So now once we do that, the continuum representation of interaction energies could be described by these integrals, and we can calculate them and evaluate the interaction schemes. So I will not go into the details except to say that the results are again described in terms of hypergeometric functions, and the numerical calculations are all implemented by writing codes in Maple. We can also have a discrete continuum model description. We can say that, okay, we model the carbon ring as a discrete cluster rather than a circular ring of uniform density of carbon atoms. Okay, the reason is simple again, because we have a very tiny carbon cluster. Quantum mechanical effects are going to be extremely important And therefore, sometimes you may lose on some of the key contributions by resorting to a continuum model description. So we would like to ideally test these results using a discrete continuum description as well. So the numerical values of atomic line densities could be evaluated. The radii of each of the carbon rings were got from electronic structure calculations in our approach. And here are the results. May I know how much time do I have?
Maybe 5 more minutes.
5 minutes? All right, thank you. Let me summarize what our findings give us in terms of the energetics. So what we have shown is that when we have a carbon ring getting adsorbed on a graphene sheet, we have 3 primary modes of adsorption. One is a perpendicular orientation, one is a tilted orientation, and a parallel orientation. So as a carbon ring approaches from very far, what happens is that the ring prefers to adopt a perpendicular orientation. And as it comes closer to the graphene sheet, it switches over to a tilted configuration. And eventually, when it comes closer towards the equilibrium geometry, it prefers a parallel orientation. Okay, and it can be easily rationalized by saying that, okay, at every stage, the ring tries to have maximum favorable interactions from the graphene sheet. The energetics all reveal it very clearly. So again, I will not get into these details, except to say that we could do the same analysis in the case of carbon nanotubes. And what happens here is that in the case of carbon nanotubes, we have the ring coming in at a particular value of axial distance, and the ring also coming in with a particular orientation. So we have energy being dependent on not just the radius of the carbon nanotube, but depends on the orientation at which the ring arrives at the carbon nanotube. So this analysis actually enabled us to develop the potential energy surface for the carbon ring getting encapsulated into a carbon nanotube. And if we get to the minimum of the potential energy surface, that is the anticipated global minimum for the system. And our continuum modeling approach actually gives us a way of getting to the potential energy surface, scanning on the potential energy surface to get to the global minimum. And this procedure is rather unique in our opinion, because any ab initio or first principles calculations are computationally intractable. And if you would like to generate such a potential energy surface using ab initio calculations, it is next to impossible. Okay, because modeling carbon nanotubes itself is rather complex. It takes a lot of computer time. And in such context, continuum modeling is extremely useful. Just to give you a feel for the experimental aspect that I was talking about, Anderson and co-workers in the last year actually have reported the experimental synthesis of C18 carbon ring, which they have called as cyclo-18 carbon. And this was reported to be made on an NaCl substrate, sodium chloride substrate. Okay, and we had predicted that such carbon rings could be made by isolation on graphene. In fact, we are happy to note that there has been a recent review in Chemistry European Journal, which says that computational modeling of cyclocarbons pointed out the possibility of their deposition on graphene, which refers to our work. Anderson and co-workers most recently succeeded in the generation of cyclo-18 carbon and its observation by using a microscope. This is what refers to the science paper in 2019. So we are quite happy that the modeling approaches are indeed helpful for designing new experiments for isolation of these carbon clusters. In our group, we have also been quite interested in understanding permeation through carbon membranes. Now, the reason why this is extremely important is one might at the first look say that, okay, what is so special about permeation? It is as simple as if you have a blue ball out here and a pink ball out here, and if you have a porous architecture, and if you choose the right pore, it is perhaps possible to let in the pink ball while block the blue ball. Okay, it is as simple as a classical size sieving mechanism. All right, but the reality is not so simple. Today, it is possible to design smart membranes that can actually enable us to separate isotopes. Indeed, in our group, we have shown that it is possible to separate helium-3 from helium-4 by designing a smart membrane of this kind. Okay, other researchers have also demonstrated excellent smart membranes that can actually even separate enantiomers. For example, the idea is what I will talk to you in a few seconds. So typically, if you have a membrane like this, and if you have two enantiomers, you can design one of the entities at the pores such that it kind of combines with one of the enantiomers while letting in the other enantiomer to the other side. Okay, these are typically smart membranes, and this molecule out here at the membrane is what is referred to as a bouncer. So this guy actually bounces off one of the enantiomers while letting in one of the other enantiomers. So these smart membranes are extremely important, and our group also has contributed towards probing the selective permeation of fullerenes through these interesting materials called graphines. And we have shown that fullerene permeation through graphines can lead to interesting oscillatory motion, okay, which could perhaps be seen in experiments, and happy to note that this work featured on the Young Scientist cover issue in Journal of Physical Chemistry. So I would like to close the lecture by thanking all my group members who have contributed enormously for the understanding that we have today. And special thanks to my graduate students, Ovais, Chris and Anto, who have been extremely effective in implementing all these models. And the funding of our research is through various funding agencies as given here. I'm grateful to them for their support. And finally, I would like to close by thanking all of you for your patient listening. I would be happy to have any questions that you may have.
Thank you very much, Professor Swati, for this wonderful talk and walking us through those continuum and atomistic model methods you use for the carbon nanostructures. We are actually running out of time, but I think still we can take maybe one short question.
Good morning, ma'am.
Yeah, good morning.
I am Dibyajit. I'm speaking from Jorhat Institute of Science and Technology, Assam. Actually, I'm new to this field. It's a very interesting lecture. I have for the first time listened to this kind of computational chemistry lecture. So it's a very interesting work you have done by your group. So so my question is, what is the software you basically use for these carrying out this research work?
Okay, so a lot of our calculations are actually written in Maple and Mathematica. So we actually write codes for all these calculations, and sometimes we employ Mathematica for writing our codes. Sometimes we employ Maple. Okay, actually, so these are not commercial softwares for electronic structure calculations, for example.
Time for a short question.
Actually, I'd like to have suggestions from your side. What software I should learn so that I can do work in computational chemistry.
Okay, so what I would suggest is you need to pick up a bit of programming, which could be done using Python or Mathematica or MATLAB or Maple. All of them are equivalent. Python, of course, is a programming language, but Mathematica, MATLAB, and Maple are kind of algebraic packages. Okay, I would recommend highly using Mathematica or MATLAB, which are easily available. And if you are interested in electronic structure, of course, Gaussian is one good software that you could attempt looking at.
Okay, thank you, ma'am.
Yeah, I see Professor Padmanabhan. Sir, we have 2 minutes only.
Oh, okay.
No, you can ask.
Yeah,
yeah. You can
this is
ask, but 2 minutes.
Dr. Fadi, wonderful presentation.
Yes, sir.
Can you hear me? Okay.
Thank you.
Thank you for accepting our invitation. Simple question. I mean, you talked about the organ, rather absorption through, or rather, take up by the nanotube. Rather than the absorption, perhaps the transport would be more interesting, because especially for separation of the noble gases. My concern is there any kind of a barrier if the noble atom transports inside the nanotube? Say, for example, one time it may be above the ring, and of course it has to pass through the bond. So is there a barrier between them, or does it sail through without any kind of a barrier?
No, there is a barrier. If you look at even graphene or carbon nanotube, even a small atom like helium cannot go through the hexagonal ring. There is a huge barrier.
Not through the one. For example, carbon nanotube actually from one end to another one, transport.
Yeah. That is what we have looked at. Like encapsulation into carbon nanotubes is through the one-dimensional direction.
How much is the barrier? Is it very... so one has to think about the temperature also. Maybe you do it in a very low temperature. There will be temperature effect also. Is that sufficient to surmount the for easy transport of that one?
Yes, yes. In case of carbon nanotubes, yes. In case of graphene, of course, you know that graphene is impermeable to any of the... Yeah. That is why we have always gone to graphene nano meshes, you know, where you drill pores and make the pore a bit larger so that it permeates through. Yeah.
Thank you. Thank you.
Okay.
Thank you.
Okay. So let's all thank Professor Swati for her wonderful talk. Thank you. Thank you very much, Professor Swati. So now we'll move to our next talk. Our next speaker is Dr. V. Ganesh from CSIR SICRI. I see Dr. Ganesh. I think he's online. Okay, I request Mrs. Rajita to give the brief introduction about Dr. Ganesh.
Good morning and welcome all to the fourth keynote talk on the second day of ICAMSC 2020. The speaker of the session is Dr. V. Ganesh from CSIR SICRI, India. It is indeed a great pleasure for me to introduce Dr. Ganesh. Dr. Ganesh obtained his PhD from Raman Research Institute, India, and he did his postdoctoral fellowship at the University of Edinburgh, Scotland, UK. He was a visiting researcher at the University of Manitoba, Winnipeg, Canada. In 2009, Dr. Ganesh joined as the principal scientist at the Electronics and Electrocatalysis Division, CSIR SICRI, India. Dr. Ganesh's research areas are electrochemistry, surface chemistry, electroanalytical chemistry, electron transfer studies across electrode-electrolyte interface, biosensors and bioelectrochemistry, electrochemical enzymatic catalysis, self-assembled monolayers, its structural aspects and applications, electrochemical tools for healthcare diagnostics, electrochemical studies using microemulsion and liquid crystalline phase systems. Dr. Ganesh has been granted many research project from CSIR under Empower Scheme, DST under Technology Systems Development Program, and DST under the Fast Track Proposal for Young Scientist Scheme. In 2011, Dr. Ganesh nominated for CSIR Young Scientist Award in Chemical Sciences by CSIR. He is an active member of the Society for Advancement of Electrochemical Science and Technology, Karekudi, and Electrochemical Society, USA. He has published several research articles in reputed national and international journals in the area of electronics and electrocatalysis. With this brief introduction, on behalf of the organizing committee, I welcome you, sir, to the first international conference on advances in material science and chemistry to deliver the talk on the topic Electrochemical Biosensors for Clinical Diagnostics, Multidisciplinary Research Perspectives. Over to you, sir. Thank you.
Thank you, ma'am. Yes, Naveen, yeah, I'm here.
Yeah, you can upload the PPTs.
Yeah, I'll just share my just give me a minute. I'm just trying to load. Yeah.
Okay. We can see.
Yeah. Can you?
Yeah.
Yeah.
Please put them on the slideshow now so that.
Yeah, sure. Very good morning to all of you. First of all, I'm thankful to organizers for giving me an opportunity to present my research work in this international conference. I would like to thank Dr. Beena and Dr. Naveen I think, who have made a valiant effort in organizing this conference and taking care of us for this presentation. Today, I'll be talking about electrochemical biosensors for clinical diagnostics. And during the course of my talk, I will try to highlight the importance of multidisciplinary approach. Okay. So before I begin my lecture, usually I talk like where do I come from and who am I, and then slowly I get into my lecture. Okay, so my target audience is mostly students and people who work in the area of electrochemistry and biosensors. Okay, on a very lighter note, why I start by saying where do I come from is because Karaikudi is located in southeast of Tamil Nadu, which is very near to both Madurai and Rameswaram. One day I went for a haircut, and in a typical Tamil slang, the barber asked me, "Sir, where do you work?" Then I said, "I work in a place called Sikri." Then the spontaneous question from the barber was, "Do you guys make atom bomb?" I was very surprised to hear such a question from barber. So from that moment onwards, I decided wherever I go and wherever I give a lecture, I start from where do I come from. Okay. So of course, Central Electrochemical Research Institute, profoundly known as SICRI, is located in Karaikudi. This is one of the constituent laboratory of CSIR, which is Council of Scientific and Industrial Research. We have headquarters located at Karaikudi and 3 different subunits. One is at Chennai, Tuticorin and Mandapam. We are roughly about 400 employees, out of which 1/3 are scientists. And we have various divisions covering all the aspects of electrochemical science and technology. Even now, SICRI is one and only research institute in India completely devoted to the research in the field of electrochemical science and technology. So we do look at fundamental aspects of electron transfer reactions across electrode-electrolyte interface, and we design material for tuning such electron transfer reaction. And we come up with small prototype, device instrument for multifunctional applications. And if you look at the history behind SICRI, the foundation stone was laid in the year 1948 by then Prime Minister Sri Pandit Jawaharlal Nehru ji, and it was declared open in the year 1953 by then President Sri Sarvapalli Radhakrishnan, and he is Dr. Bhatnagar, who is the founder of CSIR, I would say, and the man in between the two is called Dr. R.M. Alagappa Chettiar, the great philanthropist belonging to this part of Tamil Nadu, who has donated 100 acres of land and 15 lakhs of rupees in 1950 itself to establish such an institute. Okay, so it's been about 7 decades, and the contribution of SICRI to both in the field of electrochemical science and technology and to the national growth is enormous. I can highlight many things, but maybe a very few. The corrosion prevention coating given to a Bomban bridge, which is connecting the mainland India to the island Rameswaram, is given by SICRI. And apart from this, we developed many ion selective electrodes, a sensor for hemoglobin, etc. To the recent addition being 100 unit cell per day fabrication facility of lithium ion cells at Chennai. Right. That's about institute. As far as I am concerned, basically I am a chemist. I do work on electrochemistry. It's my bread and butter, and I do take concepts from material science and biology to come up with sensors and devices, mainly for energy and environmental applications and for biomedical applications. Right. So how am I going to give this lecture? Right. So initially, I will try to highlight why one has to worry about doing research, and I will go by classical book-based definition of what sensor is all about. Then I will highlight a little bit about electrochemistry, and during that point of time, I would like to highlight what is the importance of electron transfer reaction. And how do you modulate such electron transfer reaction through multidisciplinary research strategies? And once you tune such electron transfer reaction, we can bring in applications in many different fields, including biosensors, electrocatalysis, energy conversion and storage devices, etc. I will also try to highlight, suppose if you introduce many different nanostructured materials, what effect it can bring in to biosensor application. Right. Now, this is the slide where you can see that the top 10 problems which humanity will face in the upcoming 50 years or so are listed down. People are involved in doing research to find solution to these global issues. If you look at these top 10 problems, we have energy, water, food, environment, poverty, terrorism, disease, etc. Okay, I can give examples for each of these problems that which is going to be very critical in the upcoming 50 years or so. For example, if you take energy, for example, about 5-6 years ago in Tamil Nadu, we have 14 to 15 hours of power cut on a single day. So you can imagine in a day of 24 hours, 14-15 hours of power cut. So how a state would progress, And apart from this, India is digitalizing. So we moved from a classical blackboard based teaching to online virtual mode based teaching. So everyone uses laptops, computers, mobile phones, etc. So the batteries, which is a critical component of these devices, comes under the energy storage device. So energy is going to be a very critical issue in the upcoming 50 years or so. Not just that, you can take any house in a village, there won't be any house in a village without the following 3 items like laptop, TV, mobile phones and two-wheeler, So energy is going to be critical. Of course, since I am going to talk about today biosensors, let me give an example of a disease. About 2 decades ago, if we get a fever or ill, we go to a single doctor and the doctor would give us an injection or a tonic. Then the next day, we guys would be feeling happy and then, start doing our regular activities. But nowadays, there are plenty of newly nominated disease, I would say, and we have to find solutions. How do you tackle such kind of disease related issues? Okay, apart from this, the human population across the globe in the year 2012 was estimated to be 6 billion, and it is expected to grow roughly twice by 2050. So we need to provide them clean energy, good drinking water, sufficient green environment for our generations to live, right? How do you find solutions to all this problem? The one and only way to find solution to this problem is through science and technology. And I would go one step ahead and say that electrochemical science and technology can provide solution to each of these problems. And when we find solutions, we make a small step towards self-reliant India as the dream of our Honorable Prime Minister Sri Narendra Modi ji. Now, when you want to develop biosensors devices or biosensors as a whole, we need to understand how this chem-bio interface work. Let me tell you a small story so that I can bring the importance of understanding this chem-bio problem to solve an issue, right? So when we play, normally we guys during the break take glucose as a drink to get spontaneous energy. The moment you consume glucose, since delta G, Gibbs free energy of the reaction is negative, through classical book-based equations where glucose undergoes oxidation to give you 6CO2 plus 12H2O plus energy, and we get energy in terms of ATP release, right? So let me ask you a series of questions for you guys to just think about it. Let's say we all have good food in the night and we go to bed to sleep and we wake up in the morning. So who asked us to wake up in the morning? let's say disturbance from mobile phone, husband, wife, etc. Once you wake up, we get ready, maybe let's say in a couple of hours or so, and we feel hungry. And why do we feel hungry? And let's say we consume breakfast, we take breakfast and we go to a bus stop to catch a bus to university or institute. When you look at someone else, we feel happy, and when you look at someone else, we feel very much irritated. We express emotions. All these things happen because of, you guys would say, a biochemical reaction which occurs in our body. I would go one step ahead and say that all these reactions happen because of electron transfer reaction which occurs in our body. The moment I say that it's due to biochemical reactions, some biomolecules undergo oxidation, some others would undergo reduction. So the moment this redox reaction comes into picture, electron transfer exists there. So a study which deals with such kind of electron transfer reaction is nothing but your electrochemistry. And once you modulate this electron transfer reaction, you can even modulate human behavior as a whole itself. Now, if you look at classical book-based definition, what sensor is all about? Sensor is nothing but a device which converts either physical or chemical parameter into a measurable electrical signal. And in general, it comprises of sensing element, transducer, and connected electronics. To understand this, for example, you guys would have seen a glucometer which is available in the market. What do? That meter is in fact used to measure how much glucose is present in our blood serum level. You can prick your finger, take a drop of blood, put it on a flexible disposable strip, and the moment you place a drop of blood onto that strip, you insert that strip into a device. The device then is nothing but an electrochemical small equipment which gives you a reading, and that reading is correlated directly with the amount of glucose present in our blood. Now, how that instrument works? In fact, that is a typical example of a device which is being developed using a multidisciplinary approach, right? The flexible strip has an enzyme called glucose oxidase, which converts glucose into gluconic acid and hydrogen peroxide. The moment you insert that strip into the device either oxidizes hydrogen peroxide or reduces hydrogen peroxide so that it measures the current, and indirectly the amount of hydrogen peroxide is correlated with the amount of glucose present in your blood serum level. Now that's a typical sensor components we would describe in the biosensor device. Now this is a flow chart which gives you an idea about what in general a chemical sensor should have. It should have a recognition site which can pick up either the change in the ionic concentration or electron transfer reactions as a whole, or even it can pick up changes in temperature or intensity of light, etc. And the transducer will convert those changes into a measurable electrical signal through clever electronics. And in case of electrochemical sensor, they are nothing but a device that interacts either chemically or electrochemically with the analyte and produces a signal that is being monitored electrochemically. I'll show typical examples during the later part of my talk. Okay. The simple techniques being used in monitoring such kind of binding events of analytes are potentiometry, amperometry, and conductometry. In case of potentiometry, the measured potential is directly correlated with concentration of the analyte. And in case of amperometry, the measured current is directly correlated with the concentration of the analyte. And in case of conductometry, either you can measure resistance or conductance so that the concentration of the target analyte could be directly correlated. Now, these are the typical characteristic of an electrochemical sensor should have. For example, the sensor should be very specific. The glucometer, what I talked about a while ago, should be very specific to glucose alone. So that's the selectivity comes into picture. And we need to use a small amount of analyte, small volume samples to measure the target analyte. And it comes in handy if the device is disposable, reusable, and renewable. apart from this, the response time of such device should be very quick, And in case of biosensor, we can use biomolecules like either an enzyme or antibody, microorganism, or cell as a whole itself as a molecular recognition element, so that you can measure the changes I highlighted a while ago, like pH, temperature, light, etc. Depends upon what parameter we measure, the corresponding technique would be different to measure the electrical signal to detect the binding events. Now, those are very fundamental aspect of what sensor is all about. Since I'm going to use electrochemistry as a technique or as a tool to monitor this binding event, I thought let me highlight a few points of why electrochemistry is such a important technique. In fact, it deals with the study of electron transfer reaction at interfaces. In general, it deals with two different kinds of reaction where in one case, voltage is applied to drive a chemical reaction. That's a typical example of fuel cell comes under that category. And in the other case where voltage is generated because of inbuilt chemical reaction. Typical example being battery comes under the second category. Now, if you look at the classical definition of where does the potential originates from, if you dip any conducting rod into an electrolyte, it exits at solid liquid interface, electrode electrolyte interface, there is a spontaneous formation of this electrical double layer. And this leads to a parameter called capacitance that is correlated with potential through an equation C is equal to Q by E, right? And when the system is perturbed from the equilibrium, even the formation of double layer itself is a perturbation to the system at equilibrium. And to satisfy this Lee-Chatelier principle, the system responds. The response comes in terms of current. Okay, the current essentially originates from three different modes of mass transfer like diffusion, migration, and convection. And all the equations in electrochemistry are derived based on the assumption that diffusion is the predominant mode of mass transfer. Okay, a typical peak-shaped voltammogram, what you usually observe in CV, cyclic voltammetry technique, is due to diffusion, right? And in general, if you look at it, an electron transfer reaction will occur in the following way. Let's assume that we have a redox probe dissolved in the electrolyte, and we have an electrode which is immersed in this electrolyte. The molecules has to diffuse from the bulk to the interface, get adsorbed on the electrode surface, and it undergoes electron transfer reaction either by donating an electron to the electrode or by accepting an electron from the electrode, and it gives you a product. The product has to desorb and diffuse back to the bulk of the solution, right? So among these processes, whichever process is slower is called a rate determining step. And usually diffusion of ions from the bulk to the interface is slower. And that's why you get a typical peak-shaped voltammogram as an output in cyclic voltammetry. So we normally use three different electrodes like reference, counter, and working electrode. The applied potential will flow between reference and working, and the resultant current will flow between working and counter electrode. Now, why electrochemistry is such a powerful technique is because you know this equation, which is Gibbs free energy equation. Delta G is minus N of E. For a given process, both N and F are constant, meaning the number of electrons and Faraday's constants are constant. The only variable parameter being potential. So the moment you apply a potential, you can tune delta G from a non-spontaneous to spontaneous reaction. A typical example being a water splitting reaction. Thermodynamically, the splitting of water into hydrogen and oxygen is not allowed. But the moment you apply 1.23 volt, you can split water into hydrogen and oxygen so that both could be used as a fuel. In case of electrochemistry, apart from the usual parameters like concentration, temperature, pressure, etc., to tune activation energy and in turn delta G, right? Now, if you look at the double layer structure, the typical thickness of the double layer is of the order of nanometer. And all the electron transfer reactions what we are investigating in electrochemistry occurs within that interface. You can imagine how much is the electric field which felt at that interface. Even if you apply, let's say, about 100 millivolt within this nanometer level distance, the electric field felt at this interface is huge. 100 millivolt divided by 1 nanometer, you would get about 100 into 10 power 6 volt per meter. That's why many reactions which are not possible by classical chemistry route, we can carry out such reactions using electrochemistry. That's the powerful nature of such electrochemistry. Now, apart from this, we have a variety of techniques that can understand the system at equilibrium and deviation from equilibrium, etc. For example, the techniques like potentiometry, what I mentioned a bit earlier, is an equilibrium technique where you directly measure the open circuit potential and correlate with the concentration of the analyte. You can measure not just potential, you can measure change in capacitance, change in surface tension, etc. And when you deviate from equilibrium, a small perturbation is applied. The techniques like electrochemical impedance spectroscopy, pulse voltammetry, etc. Those techniques comes under the transient techniques. Okay. Apart from this, when you move far away from equilibrium, then also you can able to understand how the electron transfer reactions occur at this interface through techniques like cyclic voltammetry, linear sweep voltammetry, etc. That's the powerful nature of such electrochemical techniques. Moreover, you can couple these electrochemical techniques with fancy techniques like even spectroscopic hyphenated techniques you can bring in, so that you can able to cross validate the parameters you measure, and also you give a kind of whole understanding of the mechanism behind such electron transfer reaction. Now, coming to the area of research what I work on, I will show you typical examples where we developed the biosensors for a potential biomolecule through development of detection strategies, designing molecules and materials for the target analyte, and also the sensing platforms. Okay. In fact, in our group, we started developing biosensors using self-assembled monolayer, which involves, in fact, the formation of a single layer of molecules on the electrode surface through spontaneous chemisorption process. Why self-assembled monolayer? Well, it is very easy to prepare, and it forms a very organized, molecularly ordered structure.
Dr. Ganesh? It seems it's stuck. Dr. Ganesh?
Probably got disconnected or?
I'll call him on phone. Check. There's a lot of rain in Tamil Nadu as well, so maybe the network issue. Dr. Ganesh?
Naveen, are you calling him?
Sorry for the inconvenience. There was a network issue, so he'll be joining us again in 1 minute or so.
Could you talk to him? Or okay.
Yes, sir. I called him. He'll be joining back. Dr. Ganesh? Dr. Ganesh, can you hear me?
Yeah, can you hear me now?
Yes.
Hello,
yes,
Naveen.
Yeah. Yes, we can hear you.
Okay. Yes, sorry, there is a just a network issue with the institute, I guess. Just give me a minute, I will load my presentation. Is it okay?
Yeah. Okay. Yeah. No problem.
Can you, I'm just trying to share the file.
Okay. Dr. Ganesh, can I try from my side? I have the PDF files.
Yeah. If you could load, then it is okay. Yeah. Thanks for it. Yeah.
Okay. Yeah, I'll try that maybe.
I don't know whether you have to make me as a presenter. Not necessary, is it? I'm trying to share the file, but
no,
it doesn't matter.
That permission is given to you, but anyway, let's try this.
Okay.
Can you all see the PDF?
You can load the files, so no problem. I'll make a presentation from here.
Okay, you please tell me where we were. So basically,
SAM self-assembled monolayer. Just I completed the introduction, I guess. The moment I get back to my research, I think power went off. Yeah.
Okay. This
just maybe a couple of slides before LPS sensing. This could be.
Sorry, it's not clear.
Just a couple of slides before LPS sensing.
Okay.
The one.
Okay, just slide before LPS sensing. Okay, here it is.
Yeah. It's all right, even if it is LPS, no problem. Yeah.
Okay, I think we'll go to LPS because we can save some time. Okay, sir. Yeah.
Okay. So we started our research using self-assembled monolayer. As by the way, I'm very sorry that I was anticipating this problem earlier. That's why I sent a backup slide to Dr. Naveen. So it's good that Naveen had the slide and he could able to load, I guess. Now, we started our career of developing biosensors using self-assembled monolayer. So I was trying to explain that it forms an appropriate framework to investigate electron transfer reactions. And you can also use this self-assembled monolayer as a platform to develop biomimic catalysts. Okay, you can mimic the function as well as the structure of the biomolecule we interested in. Also, when you change the length of this molecule used for forming a self-assembled monolayer, you can able to tune the electron transfer reaction. For example, for a given length, the aromatic moieties mediate electron transfer reaction much faster than the aliphatic moieties of similar length, right? So, the idea of SAM, we developed a sensor. We developed an electrochemical biosensor for lipopolysaccharide. You can look at the structure here, which is an interesting molecule, because this provides information about immune response of humanity. Let's say, for example, a person met with an accident. Immediately, he or she has been taken to ICU, and there they basically want to measure, want to analyze whether the patient will survive or not by looking at how much LPS is there in the system. In fact, depending upon the concentration, initially it leads to organ failure, and ultimately it leads to septic shock, what is called self-poisoning of the body. if we look at the structure of this molecule, which is very interesting, it has a long aliphatic chain and sugar moieties. Apart from this, we have functional groups like phosphate or carboxylate to target. So what we done is we developed a receptor for each of these components. Okay, so we used the Sam. Naveen, could you go to the next one, please? So we used self-assembled monolayer to anchor these molecules hydrophobically on the electrode surface, so that you can add the receptors to each of these components. We can add receptors to each of these components and investigate the binding events. Naveen, could you go to the next slide, please? Yeah. So this molecule is highly toxic because of the negative charge associated with this molecule. Okay. So when these receptors go and bind to each of these structural components, the negative charge of the molecule is neutralized, and hence the toxicity is reduced. Now, using a hydrophobic interaction, these molecules are anchored on the electrode surface, and when you add a receptor to each of these structural components, we can monitor the binding events using charge-based redox. In fact, we use the electrochemical impedance spectroscopy to monitor this charge-based interaction. And you can see that the molecules, when it goes and binds to the system, the RCT, charge transfer resistance of the molecule, comes down, which in fact tells you the charge-based interaction occurs. There are many challenges involved in developing this biosensor. This is an example where we developed a detection strategy. We come up with a concept called complementary pattern-based recognition receptors. You know, when I described about the structure of this molecule, which has different components, and we can consider them as pattern, and these patterns are complementary to each other. Now, go to the next one, please, Naveen. Thank you. So, based on this concept of complementary pattern-based recognition receptors, we can monitor the binding events and measure the impedance to probe charge-based interaction. This kind of detection strategy we come up with. Can you go to the next slide, please? Now, depends upon the target analyte, and also design the molecule as a whole. If you look at Naveen, can you go to the next slide, please? Yeah. So when you look at the molecule, we have a binding domain with thiolate moiety, so that this molecule should go and anchor on the electrode surface. And we have a spacer regime where you can mediate the electron transfer across this interface. And on top of the molecule, we have a citadel unit where the metal ions can go and bind to the system directly. Now, using these molecules, we come up with a concept called metal-mediated electron transfer reaction, where in the case of copper, the electron transfer is mediated across this interface about 600 times higher than the corresponding one with the ligand alone. And if you go to the next slide, you would able to understand. Can you go to the next one, please? So these molecules, then when in the absence of metal, there is no electron transfer reaction. And the moment you introduce metal, this molecule mediates electron transfer reaction across this. And you can measure the rate of electron transfer reaction using cyclic voltammetry and the electrochemical impedance spectroscopy. Can you go to the next one, please? And we can develop sensor by altering this electron transfer reaction by throwing in ions like anions. For example, in this case, specifically, we developed a sensor for cyanide, which specifically goes and binds to the copper moieties, and copper is being removed from this ligand so that the charge transfer resistance is enhanced. And specificity comes in because of the metal analyte interaction. That's the strategy we come up for developing a sensor for. Naveen, could you go to the next one, please? Slide. You can move. Naveen. Based on these strategies, we have come up with sensors for science. And in fact, apart from electrochemistry, we have also developed a sensor using fluorescent-based technique too. We can, functionalize the fluorescent molecule in terms of nanoparticles and quantum dots. Naveen, could you please move the slide? Sorry. Naveen, could you move the slide, please? Yeah. In the case of fluorescent-based system, using an electrochemical method, we come up with a simple strategy where you use graphite anode and a platinum cathode. We use a simple electrolysis process in which we can simultaneously prepare reduced graphene oxide and fluorescent graphene quantum dots. Okay. By altering the time duration allowed for electrolysis process, and we can add a reducing agent upon the time allowed for a reduction process, you can able to tune the size of the resultant graphene quantum dots, in turn different emission colors like green, blue, yellow, etc. Naveen, could you move the slide? Probably that will tell you the idea. Hello, Naveen. Right. Using this electrolysis process, we get a precipitate which is settled at the bottom, and the supernatant is a liquid where you would get the graphene quantum dots. We used both this, reduced the graphene oxide and graphene quantum dots for sensing as well as the energy conversion and storage applications. Naveen, could you please move the slide if possible? Naveen, could you please move the slide? Yeah. We utilized certain graphene quantum dots for bioimaging applications and for reduced graphene oxide as supercapacitor applications. Apart from this carbon-based fluorescent material, we have also made an attempt and developed a sensor for small molecule like cysteine, hydrogen peroxide, etc., using fluorescent gold nanoparticles. In fact, we used an enzyme called glucose oxidase and utilized the redox property associated with that enzyme. Recall FAD-FADH2, flavin adenine dinucleotide, and the protonated species of this to reduce a metal salt into metal nanoparticles, and that emits fluorescence. Naveen, could you please move the slide? Please move the slide. Hello. Naveen, could you please? Yeah, could you please move the slides?
Yes, I see. I have moved it, but I think maybe there is a time lag.
Okay, yeah. This is the kind of strategy we adopted for gold nanoparticle fluorescence emission. Okay, interestingly, when you use an enzyme to prepare such fluorescent gold nanoparticle, that emits yellowish green fluorescence in case of neutral pH. And when you switch over the pH to acidic and alkaline, you can tune the emission colors into either green or rosy red, etc. And since it is a fluorescent-based sensing, you can able to quench the fluorescence by developing a sensor for a small molecule like cysteine, an important amino acid. when it goes and binds to this gold nanoparticles, it leads to an aggregation of individual nanoparticles, and thereby the fluorescence is quenched. And using this strategy, we have developed a sensor for both hydrogen peroxide as well as the cysteine. Now, these are the methods we adapted using the molecule as well as the material by designing them for a target biosensing applications. Apart from this, we also worked on developing a flexible sensing platform for biosensor applications. I couldn't see the slides actually moving in this. Are you moving? Maybe it's only my problem or the system. I'm not able to see the slides. Yeah. Now, you can load the slides where the flexible sensing based platform being developed. For example, we used OHP sheet, overhead projector sheet, and we employed an electrochemical method of modifying this OHP sheets, and we employed them as a disposable strip for both glucose sensing, and a slight modification in the strategy where we deposited silver followed by zinc oxide, and we used such a strip for sensing of pesticides. Now, in this series, recently we started working on human sweat analysis. The glucometer, what I talked about a while ago earlier, which involves invasive technique, meaning you need to prick your finger, take a drop of blood, and use the flexible strip to detect the amount of glucose present in the solution. In contrast, we have come up with methods where we can analyze such kind of biomarkers directly from human sweat itself. When you talk about sweat, which is an interesting concept, which is called perspiration, under two conditions a human being would sweat. One is the temperature difference, thermal gradient, and the other condition being emotional changes. Okay, suppose a teacher comes into class and says that today we are going to have a surprise exam, then the students get agitated, then they start sweating. So such kind of emotional changes would also induce perspiration. And the constituents under these two conditions differ in case of sweat, and you can able to analyze the constituent like urea, glucose, lactate, etc. from sweat itself. So we have come up with a strategy where you can design the flexible strip. You can create a multiple array of electrodes on this flexible strip so that individual array could be used to address the individual analyte, so that in a single platform you can able to detect multiple analyte and you can correlate with the disease, right? Glucose, for example, diabetics, and urea, you can understand the kidney dysfunctions, and lactate, for example. Apart from this, we also know that there are constituents like Na plus and Cl minus in sweat, and you can measure the ratio of Na plus and K plus, which is a very good biomarker to understand the cardiac related diseases. Okay. Chloride, which is also used to understand genetic disorder. That's a disease called cystic fibrosis. So even now in clinic, people used to understand this genetic disorder by measuring chloride concentration from sweat itself. So that's the kind of strategy we adopt, where we have developed flexible platforms using OHP sheets. Using screen printed electrode, we developed a multi-array of electrodes to address this. Now, the same concept could be extrapolated to both defense and sports based applications. I can maybe give a small story and then maybe wind up my presentation, right? In case of sports, we guys would know that let's say, for example, Olympics, you conduct a 100-meter race. How you would analyze whether a person is being taken drug or not? has taken drug or not, you collect either his blood or urine samples before the race start and after at the end of the race, or and to announce the result. Normally it takes about a year or two. By then the person would have been already got a lot of sponsorship and earned money on his own. Now that is not a right way to analyze this. The idea being, you can impregnate this array of sensors on the flexible strip so that during the running itself, you can able to measure these biomarkers using biocomputing process from sweat itself and directly correlate with the change in biomarker level so that you can able to predict whether a person has taken a drug or not. So using that concept, we developed the strategies for human sweat analysis. Now, Naveen, could you move the slides again? Maybe last couple of slides on MFC. How long I can talk? Or maybe in few minutes I can wind up if you wish.
Yeah, actually, yeah, 2 minutes more. I think we are running out of time.
You can corresponding to MFCs, microbial fuel cells, right? So
yes,
apart from this area, we also focus in the area of microbial fuel cell, which is an interesting concept where you can generate electricity from waste itself, right? For example, we immobilize the microbes onto the electrode surface. We simply dip them into a wastewater or even food waste, industrial waste, etc. And with respect to time duration, these microbes grow on the electrode surface, and you can connect them in a fuel cell assembly so that when you add the industrial waste, the microbes consume that industrial waste, undergoes oxidation, and during this process it releases electron. The electron would flow through the external circuit and gives you a power output. We have demonstrated using such concept. Remember, when I talk about the microbial fuel cell, these are not the system where you can generate a very high amount of power output. You can generate power of the order of, let's say, microwatts to milliwatts, so that this could be used for small power requirements. Okay, you can play with an electronics and you can assemble many cells so that you can maximize the voltage output, in turn the power output of such microbial fuel cell assembled system. Okay, so we have demonstrated not just industrial waste, even bad wine can make good energy out of it, because when the fermentation is prolonged for longer duration, the microbes can consume more amount of ethanol being produced during this fermentation process. And using the microbial fuel cell assembly, you can generate a power output of this, And to conclude, basically electrochemistry is a powerful technique. It can, when you combine electrochemistry with concepts from material chemistry and biology, you can come up with sensors and devices for a variety of biomolecules, biosensor applications. And in order to do this, we need a multidisciplinary group effort. Remember, all these things lead to kind of smart material and smart sensing that's we aim for in the upcoming years. Let's say you guys are, listening to me, sitting and listening to me, and we face a lot of these issues with power. Suddenly you get bored of my talk and you just lean on your, and the chair understands that you are not interested in listening to me, and that converts into a sofa. And that's the kind of smart material we talk about. But remember, the chair can also prick you and make you listen to me and say that, this is a kind of important topic, so that you would it would be useful for your research and so on. So that's the kind of smart material and smart sensing we talk about. And in order to do this, we need a multidisciplinary group effort, not just chemist or biologist. When you combine all the things together, we can come up with potential sensors for many different biomolecules. And finally, I'd like to again thank the organizers for providing me an opportunity, and thank you all guys for patience listening. Thank you. I'm sorry that there is an in-between power cut. Unfortunately, we had an issue here in the institute. A tree fell off and we had a lot of power issues. So I think that's why they are setting it right now, I guess. I would be happy to answer any queries, questions you guys may have. Thank you.
Thank you, Dr. Ganesh, for your wonderful talk. In spite of all these network issues, I think we were able to listen to you. Thank you very much for your time and then taking all this pain, connecting the different devices and reaching us. So I think Professor Patak she will be joining. She also had some network issues. She will be joining in 2 to 3 minutes. So we actually have time for a couple of questions. So we can go for questions. So I'll close the presentation. So.
Sure. Thank you. Yeah.
Any questions?
Hello, sir. Can you hear me?
Yes.
Yeah, please. I can hear. Yeah.
Sir, I have a doubt. From a CV, cyclic voltammetric graph, how do you find using a CV? How do you find the number of electrons which is involved in that reaction?
Very good. Right. So when you analyze CV, you can look at how the peak position and the peak current changes with respect to change in with respect to change in scan rate. If the given process is reversible, you can measure. Sorry, can you hear me? Can you hear me?
Yes, sir. Yes, sir.
Sorry, can you hear me? That your voice is breaking, I guess.
Yes, sir. Yes, sir. I can hear you.
Yeah. Now, by changing the scan rate, at least of the order of 2 magnitude change, you can able to look at how the peak position, which is the potential, and the peak current changes with respect to change in scan rate. And by employing Randall-Sevick equation, you can able to measure the number of electrons associated with the electron transfer. There are conditions one can look at if the reaction is reversible, irreversible, or quasi-reversible reaction. Okay, that's why I mentioned that when you measure how the peak potential changes or the peak current changes, you can able to predict such reaction. And using Randall-Sevick equation, you can able to measure the number of electrons. I guess I would able to answer, right? Did you get the point?
Sir. Yeah, but can we do that by comparing it with standard ferricyanide solutions?
Rasha, sorry to interrupt. So, Dr. Ganesh.
Yeah, please.
Okay, sir.
Please.
No, yeah, because you see, we are already 30 minutes running late. So I request all the participants, please, you can email Dr. Ganesh. He'll be happy to answer your questions. Or you can post it here. We'll kind of collect all the questions and send it to him. So thank you very much, Dr. Ganesh.
Thanks, Naveen. Special thanks to you for sharing the slide. Thank you. Yeah.
No problem. So this is the time to move on to our last talk of the day. We have Professor Amita Patak from IIT Kharagpur with us. I request Dr. Smita Chandran to introduce Professor Amita Patak to the audience.
Microphone not connected দেখাচ্ছে
Naveen sir, am I audible?
Yes, ma'am.
Namshivaya, it is my privilege to introduce Professor Amita Patak, Professor, Department of Chemistry, IIT Kharagpur, West Bengal. Her current research focuses on solid-state chemistry and material science, especially on the synthesis and characterization of biocompatible nanostructures for bioimaging, diagnostics, drug delivery, biosensors, and antimicrobial activity applications. She had numerous publications in peer-reviewed international journals in her credit. She had received several awards and fellowships. Some among them include editorial board member of Scientific Reports, a journal from Nature Publishing Group, her research work highlighted in Science Daily, which is critically acclaimed popular science news website. She was a member of several professional bodies. Some of these include Life Member of Material Research Society of India, Life Member of Chemical Research Society of India, and much more. We are very fortunate to have Professor Pathak with us today. Topic of today's discussion is inorganic nanostructure-based drug delivery systems for cancer therapeutics. So, looking forward to hear from you, Professor Pathak.
Yes, I've been having some problem with my network, so it has to be full screen. Can you see the full screen?
Yes, Professor Pathak. Now, if you can please put it on the slideshow mode.
Slideshow mode. Can you see it now?
Yes, yeah, now it is clear. We're set to go.
Okay. Okay, so what I'm going to talk about today is I'm going to talk about in very generic form. Whatever I'm going to discuss is just, it's a very, very big topic. So I'm going to just go from the basics because students are there. And I'm going to touch upon few of my work, but basically it will be an overview of the drug delivery systems which we have. So thank you for inviting me. It's a pleasure to join, though I had a few problems initially to join with because of the computer issues. Thank you so much for inviting me for this talk. Okay, so my topic today is inorganic nanostructure-based drug delivery system. So inorganic based structure means I'm going to talk about structures which is from the inorganic field of a branch of chemistry. But before that, let us dissect the topic. The topic is having number of things which we need to take one by one at a time. One is cancer, other is therapeutics, and then you have the drug delivery. Then comes the nanomaterial. So what we are going to be looking into is to first define what cancer is. Most of us know what cancer is. So cancer is a generic term used for a disease where you have the abnormal growth of cells. They go beyond boundaries and they evade the adjoining parts and spread into the other organs. And these can be, this cancer formation occurs where the normal cells turn into tumor cells in multiple steps. And since why we are talking about cancer, why so many people are working on it, it is because it is one of the most dreaded disease we have the world over. So when we talk about cancer and we talk about abnormal cell growth, then we need to know how the cancer cell is different from a normal cell. So let us look at the image. If you can look at the image, you can see very clearly. This is the diagram which I've taken from a publication. So you see the normal cell, how it looks, and how the cancer cell looks. So from the image, you can find out or make out what the difference is. Okay. So what happens when you have a cancer cell? What are the features or phenotypes of a cancer cell? What happens is you have a mutation in the growth protein. There are a number of growth proteins associated with the gene. Okay, so these the proteins in this gene undergo mutation, and this mutation which is associated with the growth protein. The growth protein can be of 3 types. One is going to be looking after the repair of the cell. One will be looking after the growth of the cell, and another will be looking into the death of the cell. Every cell which we are having, they are multiplying continuously. There is a cell division going on, and in the process we have also cell deaths occurring. So when you have this mutation in this growth protein in the gene, or in the growth suppressor gene in the protein in the gene, then you have unchecked growth of the cells. And when the system undergoes angiogenesis is the growth of blood vessels. When you have growth of blood vessels, more blood and more nutrients flow into it. So usually what happens when you have your stomach is full, you do not need any food, the cell will not take that food. But when you have a cancer cell, it undergoes unstopped angiogenesis. So the nutrients are continuously being pumped into the cell. They do not undergo cell death. Like every, as I said, a gene will have 3 types of protein. One will suppress the growth, regulate the growth, one will repair it, and another one will suppress the, cause the death. When there is no death occurring, then you have obviously unchecked growth. Then you have another problem with this is the signal. When you are having one type of cell in a site, they are communicating with the neighboring cell. When this signal pathway is destroyed due to the malfunctioning of the protein, then the cell which is cancerous does not communicate with the other, as if it doesn't care what is going on with the neighboring cell, and they start functioning on their own, and they lose their own functional capacity. Like, so for example, let us take the white blood cell. White blood cells, leukocytes, are supposed to be helping us in the immune system. If you have more white blood cell, you are supposed to be having more immunity. But what happens if you have leukemia? What happens? You have large number of white blood cells, but they have lost their functionality. So if you lose the functionality, then you become a cancer. They have the ability of metastasis. What is that? It can move from, usually a cell has a function of stickiness. They stick together in one side. But when they lose that, then you have this metastasis, which where the system and the cell will move from the site through the bloodstream, through the lymphatic system, to the various parts of the body. They evade the immune system. So this is one of the ways we have to check the system. If they are evading, sometimes you have the cancer occurring in your system, but it's hiding so much and fooling the immune system that you cannot detect it. They produce their own energy. When we are talking about a cell producing energy, we're talking about ATP. Through the Krebs cycle, we generate the energy. But when you are having a cancer cell, then their cell growth or the energy they are provided is through glycolysis, and that is something which is different. Glycolysis also takes place in normal cell, but they're very small fraction of it. But here what happens is majority of it is glycolysis in spite of the fact that you have oxygen in the system. What happens is it is glycolysis followed by a formation of lactic acid, and then you have the fermentation. And this is all occurring in presence of air. So they generate their energy by this. What happens when you have a cancer cell? You have lot of intake of sugar or say glucose or going into the system. So too much of sugar going into the system creates lactic acid, and that causes the fermentation, and that is how they get their energy. Their genomic and the appearance are different from the normal cells, as you can see from the picture. It is obvious that they are different in looks. their boundaries are not defined, and the nucleus may not necessarily always be more in size. They can be smaller in size than the normal cell as well, but they are usually bigger in size, and they do not look like a normal cell as it should look. They are disfigured, and they lose the genetic code which is imprinted in the particular protein. So they have this mutation drivers, which this driver mutations, they drive the mutation of this gene continuously, and you get the cancer cell generated. What happens when you look at this environment, when we are trying to address the issue, we need to know what are the factors which are going to affect, and what are the things we need to address when we are talking about a therapy of this